Hello everyone, welcome back to General Chemistry. The topic for this video is mainly going to be stoichiometry, but we're also going to talk about solutions and solubility and precipitation reactions. So without further ado, let us begin. Okay, so this time I actually have something set up for our first sheet. We're not starting from scratch today. So right here I've got a chemical equation. It's still not balanced. I wanted to do the balancing on the recording just so that we could have a nice little reminder of how to balance equations in case you've forgotten it. I would encourage you to review the last few parts of the first video if you've forgotten how to balance things, but let's take a look at this. So we've got sodium phosphate and calcium bromide reacting to form sodium bromide and calcium phosphate. So if I want to balance this, let's see. So I know the numbers of sodium and bromine have to be the same going in because they're always going to be the same going out, since there's a 1-to-1 ratio between them and sodium bromide. And I see I have sodium in sets of 3 here and bromine in sets of 2 here. So I'm going to go with the least common multiple, which would be 6. I'm going to try and go for 6 sodium and 6 bromine, and that'll be my first course of action, and if that turns out to be wrong, I'll try something else. So to make 6 sodium, I would need to double this, and to make 6 bromine, I would need to triple this. And if I do that, I've got 2 times 3 sodium and 3 times 2 bromine. So 6 of each, so 6 times sodium bromide gives us 6 sodium and 6 bromide coming out. So that takes care of the sodium and the bromide ions. Let's take a look at the calcium and the phosphate ions. So I've got 2 times 1 phosphate. Remember to treat phosphate as a group. So I've got 2 phosphates going in, and I've got 2 phosphates coming out. PO4 in parentheses with a 2. By the way, if you don't recognize that PO4 is phosphate, guess what you need to do? You need to go back to part 1 and review your polyatomic ions chart and make sure to memorize it. I did say this would be important. If you can't name these compounds kind of automatically without thinking about it, you haven't practiced enough with your nomenclature. Anyway, back to the main problem. So phosphates are balanced, and for calcium I've got 3 times 1 calcium here equals 1 times 3 calciums here. So we're done. It's balanced. Worked out perfectly. Okay, so I may have stated this before, but it doesn't hurt to reiterate it again. The stuff that goes into a reaction, the stuff that's going in, those are what we call reactants, or sometimes we also call them reagents. Anything that comes out of a reaction is called a product. And stoichiometry is all about calculating how much of one substance in a reaction you get given the amount of another substance. Some people have the mistaken belief that you're always going to be given an amount of reactant and have to calculate how much product you get for it, but that's not always the case. Sometimes you'll be given how much product you want to make and have to calculate how much reactant you have to put in to get that product. Other times you might not even have a calculation between reactants and products. Sometimes you might be asked how much calcium bromide is needed to react with 12.7 grams of sodium phosphate, for example. Or sometimes you might need to calculate one product based on another product. So you might be asked how much sodium bromide would you get in a reaction that produces, let's say, 15.8 grams of calcium phosphate. So that's typically what a stoichiometry question is. They give you a quantity of one of the substances in a reaction, and they want you to calculate the quantity of one other substance in the reaction. Both substances could be products, both could be reactants, one could be a reactant while the other is a product. So you've got all sorts of different possible stoichiometric questions that could be asked. So I'm going to call the substance whose amount is given substance A. So I'm going to call it substance A. And the substance that you're trying to calculate from substance A, I'm going to call that substance B. I'm going to call that substance B. And when you have a balanced chemical equation, what a balanced chemical equation allows you to do is derive a conversion factor that allows you to convert between moles of substance A and moles of substance B. So you are able to calculate moles of substance B from moles of substance A if you have a balanced equation. Let me write this in green. Actually, no, let's do it in peach. I think this color is called peach. If you use, and I guess I should have allotted more space for this, if you have a balanced equation then you'd be able to calculate moles of one substance from moles of another. But I just asked a bunch of examples where I gave you grams of one thing and asked for grams of another thing. So we need to be able to work with more than just converting from moles of A to moles of B. How do we get from grams of A to grams of B, for example? Well, we can convert between grams and moles. That's something we learned last time with the concept of molar mass. So it is possible to get from grams of A to grams of B if you start by doing this. So start with, I probably should have done my writing before drawing the box, but grams of A can be converted to moles of A, and moles of B can be converted to grams of B. Grams of B using the molar mass, using molar mass. So if we use the molar mass of A, we can convert grams of A to moles of A, and if we use the molar mass of B, we can convert from moles of B to grams of B. Let's see, what else can we do? Sometimes you might actually be working not with grams, but you might be working with volumes or numbers of atoms. Let's start with numbers of atoms. Or not necessarily numbers of atoms, sometimes it's also numbers of molecules. So what I'll say is numbers of particles. So what I'll say is number of particles of substance A. That could be given to you, and you could be asked to calculate the number of particles of substance B. You could be asked to calculate the number of particles of substance B. And there is a way to go from numbers of particles to moles, which is to simply use Avogadro's number. If you have 6.022 times 10 to the 23 particles of something, or formula units, or molecules, or atoms, that's what particles is supposed to represent, so it could be any one of those three things: atoms, molecules, or formula units if it's an ionic compound. You can use Avogadro's number. Avogadro's number. Similarly, if you've got moles of B, you can convert it to number of particles of B, again using Avogadro's number. Avogadro's number. Should have made more space for it. And finally, you could also be given volumes of one substance and asked to calculate volumes of another substance. I really should have planned this ahead better. I don't know if I'm going to have much space here, but let's say liters of A, or sometimes milliliters, but the standard unit would be the liter. And you could be asked to calculate liters of substance B. And to convert between liters and moles, there's actually two different ways to do it depending on what you're working with. I'm going to show an example of one of those today, and next time, No. I think 2 or 3 videos from now we'll be talking about the gas laws, and we'll see how to use volumes of gases to calculate moles of gases, and vice versa. But for now, we can use something called molar concentration, which we will talk about later on in this video. Molar concentration. I'm just going to abbreviate it cons since I don't have enough space. Molar concentration. And of course the other thing, which we aren't really going to talk about today, but it will be brought up later. Let me do it in a different color. Another way to convert from liters to moles if you're working with gases is to use something called the molar volume of a gas. I'm going to abbreviate that, molar vol. So you could also use the molar volume of a gas to convert between liters of gas and moles of gas. That is something we will see in a later video. So that's not going to be covered today. Well, it could be covered today if you're watching this after I do the gas laws chapter and you're just binge watching the whole entire series, but the point is it's not covered in this specific video. Okay, and of course you can mix and match. So you could be given, for example, grams of a substance and asked to calculate liters of another substance. So you would go from grams of A to moles of A to moles of B to liters of B, for example. Or you could be given the number of particles of substance A and asked for the grams of B, so you can go from numbers of particles to moles to grams. So any path you can take, and any path you can find on this chart, you can follow up to, I guess, 3 steps, transitioning between 4 of these boxes at most to perform some sort of stoichiometric calculation. So we already know how to go from molar mass to moles, or from moles to, or sorry, not from moles. We already know how to use molar mass to go from grams to moles, or from moles to grams. We did examples of that in the last video. We also know how to use Avogadro's number to go from numbers of particles to moles of particles, and vice versa. That was also seen in the previous video. But what we haven't seen yet is how to use a balanced equation to convert from moles of one substance to moles of another substance. And we also haven't seen how to go from liters to moles or from moles to liters. That will be covered later on in this video, but for now, let's focus our attention on mole to mole conversion. So to convert from moles of A to moles of B, you're going to need a conversion factor that comes from a balanced chemical equation. This is the whole reason why balancing chemical equations is important. So right here, I have a balanced chemical equation that gives me a whole bunch of different conversion factors. Pick any two substances in this balanced equation, and you can make a conversion factor out of them. For example, if I want to convert from sodium phosphate to sodium bromide, then my conversion factor would be every 2 moles of sodium phosphate gives me 6 moles of sodium bromide. So I'd have 2 moles sodium phosphate equals 6 moles of, can I even fit it in there? I'm not even going to risk it, sodium bromide. Okay, and I can turn this into a mole ratio. I can say there's a 1:3 ratio from sodium phosphate to sodium bromide, and I could use that as my conversion factor. I could either write 3 moles of NaBr over 2 moles, or sorry, over 1 mole of Na3PO4, or I could do the reverse. I could just have the reciprocal of that conversion factor. Let's do a quick sample calculation so that we see how that works. Oh goodness, I didn't move these out of the way beforehand. Alright, there we go. So let's say I want to convert between, suppose I have 7.50 moles of sodium phosphate. And I want to figure out how many moles of sodium bromide I can make with that. Okay, well, we have our conversion factor. So you can either use the simplified ratio of 3:1, or you can just keep it as 6:2. I think you're better off just keeping it as 6:2 so that you avoid overthinking it. But yeah, I see every 2 moles of sodium phosphate, so that's what I'm going to put in the denominator. Every 2 moles of sodium phosphate, according to my balanced chemical equation, will lead to 6 moles of sodium bromide. Will lead to 6 moles of sodium bromide. And that's it. My moles of sodium phosphate will cancel with moles of sodium phosphate, and I will get moles of sodium bromide in return. So in this case, I guess we multiply by the 3:1 mole ratio, or 6:2 if you prefer. These are exact conversions, by the way. These are exact conversions, right? We're just counting how many sodium atoms are going in and how many are going out, and we're doing the same thing for phosphates and calciums and bromides. We're just counting. So these are exact numbers, which means they have no effect on the final number of sig figs. We've got 3 sig figs times infinite sig figs over infinite sig figs. Least is 3, so we should round our final answer to 3 sig figs. So 7.50 times 3, let's see, that would be 15, and another 7.5 is 22.5, and that's 3 sig figs. So 22.5, not 22.50. 22.5 moles of sodium bromide would be produced if we went from moles of sodium phosphate to moles of sodium bromide. So basically, in this case, we just did it all in one step. So we just went from moles of A to moles of B, and we stopped there. And sometimes that's all you're going to be asked, but usually you're going to have at least 2 steps. You're usually going to start with grams of something, convert it to moles, and then convert that to moles of something else, and maybe you'll stop there. Or maybe you'll start with moles of A, convert that to moles of B, and then convert that to grams of B. All sorts of possibilities, but the longest sequence of steps you'll ever have to take with stoichiometry problems will only be 3 steps. 1, 2, 3. Yeah. So moving from any position on the left to any position on the right should take no more than 3 steps, unless we include density in the mix, which we will talk about later. Okay, so that was just one example that we could use. We can make other conversion factors, of course, between different substances. I can make a conversion factor between sodium phosphate and calcium bromide, or between calcium bromide and sodium bromide, or between sodium phosphate and calcium phosphate, or between calcium bromide and calcium phosphate. And would that be all of the possible combinations? And between calcium phosphate and sodium bromide. Yeah, so I think that's 6 different combinations. Let me think here. 4 choose 2, so that's 4 factorial over 2 factorial, which would be... No, 4 factorial over 2 factorial times 2 factorial, so that would be 4 times 3 over 2 times 1. Yeah, only 6 combinations are possible here. And if you don't know about the math that I just did, then maybe you haven't learned about factorials yet in pre-calculus and combinatorics, but if you want to research that and understand what I just did, just look up the term combinatorics. And learn about factorials. But that's stuff you're supposed to learn in your math class. So yeah, not for us, not chemistry. This is all math stuff. This is all from math class. Or maths class, as you call it in Europe. Anyway, I've got some examples ready. So we're not going to stick to this, but I do have some other examples ready that will require us to use that chart I drew up. So let me go ahead and pull up the first set of problems here. And yeah, that looks like the right one, so let's open that up. Okay, so what you've got in front of you right now is a set of problems. All of these problems have been pulled from a free open source online chemistry textbook. It's the 2nd edition of chemistry from the OpenStax website. I provided a link to that book in a pinned comment under part 1 of this series in case you're looking for that book. It's decent, but it's missing a few things that I would have liked for it to have. So not all the problems we're going to do in this series are going to come from this book. Sometimes I'm going to have to make up my own problems or pull them from other books. But you know, we'll make use of whatever good problems that this book has. So number 42 says, write the balanced equation, then outline the steps necessary to determine the information requested in each of the following. So they're not actually asking us to perform any calculations. They just want us to set it up. And I can sort of agree with this philosophy, but I can also sort of disagree with it. Sometimes when students are practicing and studying, and now I'm going a little off topic, but I think this is an important general study tip. And sometimes students will spend too much time practicing the parts that they already know how to do. So with a stoichiometry problem, I think almost no students struggle with punching in the numbers into their calculator at the very end and calculating the final result. Usually the part that you need to practice is the setup. So I kind of like the way this problem is written in the sense that it's really focused on just master the art of setting up the problem, because you already know how to multiply and divide the numbers in your calculator after you can get the setup right. And, you know, I can kind of agree with that, but also it's not really good to have your first few practice problems be incomplete problems. So we're going to do problem 42 along with problem 43, which does ask you to actually do the calculation part that you skipped in 42. So we're going to do the whole problem, and I'm actually going to modify some of the problems that we see every now and then. I might like add a part B to it if it doesn't have a part B, or just ask what I like to refer to as a bonus question. But yeah, that's how things are going to be going as we move forward. It's going to be much more problems oriented than the first two parts, so we're going to be seeing a lot of problems in all videos from here on out, or in most videos from here on out. Anyway, I don't think we need to do each and every one of these, so let's just pick a couple of them. Let's take a look at part A. It says the number of moles and the mass of chlorine required to react with 10.0 grams of sodium metal to produce sodium chloride. So I'm going to write that information down, and then we'll switch back to our camera. And of course you are expected to make use of your periodic table here to get the molar masses. So let's see, they said sodium metal with chlorine gas. So I know if I react sodium metal with chlorine gas, I'm going to get sodium chloride. So I'm just writing down the reaction, I'll balance it later. And we've got 10 grams of sodium metal, and what we want is two things, moles and grams of chlorine. We're going to have to calculate moles of chlorine anyway to get the grams, so might as well just be asking for the grams. So we want moles of chlorine and grams of chlorine. And we've got 10.0 grams of sodium to start with. Okay, let's go back to our camera. Okay, so I've written all this down. We need to balance the equation. So let's see, we've got chlorine always comes in sets of 2, so if we double this, then we double the sodium metal, and there we go, all done. 2 sodium in, 2 sodium out, 2 chlorines in, 2 times 1 chlorines out, so we're good to go. Okay, so we've got 10 grams of sodium metal to begin with, so 10.0 grams of sodium. And of course we need to convert this to moles of sodium. So sodium is our substance A, chlorine is our substance B. So we need to go from grams of A to moles of A, and then from moles of A to moles of B, and also then to grams of B, since they want the moles and grams of chlorine gas. Okay, so converting to moles, I'm going to need to bring out my periodic table. And according to my periodic table, sodium is 22.990. So 22.990 grams of sodium is equal to 1 mole of sodium. Then I need to go from moles of sodium to moles of chlorine. So according to my balanced chemical equation, every 2 moles of sodium reacts with 1 mole of chlorine gas. Every 2 moles of Na reacts with 1 mole of Cl2. And then, of course, I need to convert between moles of Cl2 and grams of Cl2. here's a place where students will make a common mistake. Every 1 mole of Cl2 is how many grams? Some students will just read it off the periodic table and think they're done, but remember there's 2 atoms of chlorine in Cl2, so whatever number you get for chlorine off the periodic table, you have to multiply by 2. Periodic table says chlorine is 35.453 grams per mole. Multiply that by exactly 2, and that's going to be 70 point something. 35.453 times 2 is 70.906. 70.906 grams of Cl2. So definitely be very careful about those diatomic elements. It's very easy to forget when you're dealing with chlorine gas, oxygen gas, hydrogen gas. Very, very easy to forget to multiply by 2 when you look up the molar mass in the periodic table. Anyway, let's go ahead and perform our conversions. 10.0 grams times exactly 1 over 22.990, so that's 3 sig figs, infinite sig figs, 5 sig figs. Between 3 and 5, 3 is the least, so 10.0 times 1 over 22.990 is 0.435 if I round it to 3 sig figs, so that's 0.435. And then, so I guess we'll go ahead and write that as moles of sodium. And 0.435 times 1 over 2, that's going to be a completely exact conversion, so 3 sig figs in, 3 sig figs out. 0.435 times 1 over 2 is 0.2175, which we have to round to 0.218. So that's 0.218, and that's going to be moles of chlorine at that point. Moles of Cl2. Okay, and that part of the screen is still visible. Just wanted to make sure. And so that's part of the answer that we want. They wanted moles of chlorine. We also want grams of chlorine, so convert 0.218 moles of chlorine to grams of chlorine. We multiply by 70.906 over 1, so 70.906 times 0.218. If I round that to 3 sig figs, that's 15.5. So I guess I don't have enough space to, well, I'll try. So that gives us 15.5 grams of chlorine. So there's one of our answers, and there's another one of our answers right there. All right. So that's one problem out of the way. Let's take a look at another one. Part B says the number of moles in the mass of oxygen formed by the decomposition of 1.252 grams of mercury 2 oxide. And let's see, so basically kind of the same thing. Only reason I feel tempted to do this is just to give you a reminder that mercury 2 oxide... Oh, never mind. I was thinking of mercury 1. Mercury 1 will show up later, so I guess it's not that important to go over it now. I did mention it in the first video, and we will get a reminder about the difference between mercury 1 and mercury 2, and the oddness of mercury 1 at a later time. Let's look at part C. Moles and grams of sodium nitrate required to produce 128 grams of oxygen, with sodium nitrite being the other product. So notice how I said sodium nitrite and I didn't just say NaNO2. Here's another study tip for you. When you see the formulas of compounds, try to say their names rather than just reading them as is. Try to come up with sodium nitrite rather than just saying NaNO2, because if you get into that habit, you will forget your nomenclature rules. I've seen students do this all the time. At the end of the year, they don't remember how to name their compounds, and they end up in a lot of trouble because they see problems on the final exam or on the AP exam or whatever standardized test they're taking, where it just says the names of the compounds in words and doesn't give the formulas, and then you're in big trouble. So don't forget your naming rules. Name any compound you can name. You will run into compounds that you don't know how to name because you haven't learned the nomenclature for them, but for the ones that you do know how to name, try and name them. Don't just read their formulas as is. So that's a little bit of study advice there, which I'm sure 90% of you are going to ignore and then regret it much later. But that's my comment on part C. All of these seem to be pretty much the same. E is interesting because it starts you with kilograms rather than grams, so I might want to do that one. And F, we've got the number of moles and mass of dibromoethane. You don't need to know how to name that yet. You'll learn that in probably the last chapter we cover. Formed by the reaction of 12.85 grams of ethene, also known as ethylene, with an excess of bromine. Yeah, all of these are pretty much the same thing, so I'm just going to do part E. Let's go ahead and do part E because that's the only one that has something interesting to it where it adds another step. So we've got the number of moles and the mass of copper 2 carbonate needed to produce 1.500 kilograms of copper 2 oxide, with carbon dioxide being the other product. Okay, so copper 2 carbonate. Copper 2 means copper has a charge of positive 2. Carbonate I should have memorized from my polyatomic ions chart. If you haven't done that, go back to part 1. You're not ready for this. Copper 2 carbonate is CuCO3. Positive 2, negative 2, I just need one of each. So copper 2 carbonate undergoes a decomposition reaction and splits into copper 2 oxide. So copper 2 is positive 2, oxide is negative 2, so I only need one of each. Plus carbon dioxide. Let's go ahead and try to balance this. I think it's already balanced. One copper, one carbon, 3 oxygen, 1 oxygen here, 2 oxygens here. So yeah, it's balanced. Okay, we're good to go. So it's completely balanced. And then they said, oh wait, you can't see what I'm writing. Silly me. You can't see what I'm writing. Okay, there we go. Copper carbonate, copper oxide, carbon dioxide. So anyway, the rest of the problem, it was saying we had 1.500 kilograms of copper 2 carbonate. And we need to calculate the grams and moles of copper 2 oxide. Oh, wait, no. Other way around. We get 1.500 kilograms of copper 2 oxide, and they're asking how much copper 2 carbonate was needed to produce that much copper 2 oxide. Okay. So there's our substance A, there's our substance B. I guess I can label them A and B if you like. And in this case, we aren't starting with grams, we're starting with kilograms, so that adds an extra step. We need to perform a metric conversion, but that's not going to be too hard to do. Some of you have already done it in your head. 1.500 kilograms of copper 2 oxide gives us, let's see, for every 1 kilogram, we've got 10 to the 3, or 1,000 grams. And I should probably include copper 2 oxide here, copper 2 oxide there. I'm eventually going to stop naming the actual substances, but for the time being, I'm just going to have this as a helpful reminder so we can keep track of what substance we're talking about. Eventually, though, I do expect you to start being able to mentally keep track of all this. So we can then go from grams of copper 2 oxide to moles of copper 2 oxide. So every 1 mole of copper 2 oxide equals how many grams of copper 2 oxide? Grams of CuO. Let's go ahead and calculate that from our periodic table. So according to my periodic table, we've got copper is 63.546. 63.546 plus oxygen, which is 15.999, and that's 79.545. 79.545 grams. And then, of course, we can convert to moles of copper carbonate. So let's see, every 1 mole of copper 2 oxide gives us 1 mole of copper 2 carbonate, CuCO3, and then every 1 mole of CuCO3 is how many grams? I guess I'll write that step down here. 1 mole of CuCO3 equals how many grams of CuCO3? So if I go ahead and try to calculate that, we've got copper is still 63.546 according to my periodic table. And maybe I should just put the periodic table in front of you guys. But I don't want to have to pull it up every single time, so maybe just do the thing I always ask you to do. Just pause this video and continue watching on another tab so that you have this handy and available on a separate tab when you need it. But yeah, there's your periodic table. I'm not going to show it as frequently as I did in previous videos just because it'll get to be inconvenient. But anyway, 63.546 for copper plus carbon is 12.011 plus 3 oxygens, 3 times 15.99. That 3 is exact, like I mentioned in the previous video. I'm pretty sure we did an example like this. But anyway, that gives me a total of 123.554 grams per mole. So 123.554 grams of copper 2 carbonate for every mole of copper 2 carbonate. Okay, let's go ahead and start crunching the numbers. So 1.500 times 1,000 is, well, 1,500. So I'm going to call that 1,500 grams of copper 2 oxide is what we have at this point. And that decimal point is important. It's to show us that we still have 4 sig figs here. The metric conversions are always exact conversions, so they have no effect on the final number of sig figs. We just keep the sig figs we started with. Then 1,500 grams divided by 79.545. So 1,500 times 1 over 79.545. 4 sig figs, exact, and 5 sig figs, so we round to 4 sig figs. That would be 18.86 according to my calculator. I hope you're following along with your calculator, by the way. So that's going to be 18.86 grams of copper. Wait. Grams? No, moles. Moles. Oh goodness, I botched this. 18.86 moles of copper 2 oxide. There we go. And I should probably stop trying to draw big brackets around this because it keeps running me out of space. I think what I'll do is I'll just write the running total on top of the last conversion factor I multiplied by from here on out. Anyway, 18.86 times 1 over 1 is still 18.86. We don't lose any sig figs because the ones are exact, so we still have 18.86, but now it's moles of copper to carbonate instead of copper to oxide. And then finally, so that's one of our answers, by the way. It was asking how many moles of copper to carbonate. It's also asking how many grams. So we've got 18.86 times 123.554 over 1. And that gives me 2,330. I still have 4 sig figs, so I would say we get 2,330, and I'll include a decimal point there to emphasize that this 0 is significant. We have 4 sig figs here. But yeah, that's the grams of copper to carbonate that would be needed in order to produce 1.5 kilograms of copper to oxide. Alright, let's look at an example that doesn't use grams, but an example that uses numbers of particles. So let's go back to here, and let me switch to that problem. Okay, so here we have a reaction that's already balanced for us, thankfully. And it tells us iodine, which I presume is going to be solid iodine, because iodine is usually solid at room temperature, though it could also exist in the form of a gas. Iodine is produced by the reaction of 0.4235 moles of copper 2 chloride according to the following equation. 2 moles of copper 2 chloride react with 4 moles of potassium iodide to produce 2 moles of copper 1 iodide plus 4 moles of potassium chloride plus, I presume, solid iodine, though you could also argue it might be iodine gas, especially if this reaction generates some heat that would warm it up from the solid state to the gas state. But that's a can of worms that we don't want to open just yet. We'll talk about solids and liquids and gases and their phase changes in a much later chapter. How many molecules of I2 are produced, and how many grams of I2 are produced? Those are the questions. How many molecules and how many grams? Well, molecules are particles, so guess what we're going to be using? Avogadro's number. So I'm going to copy down our balanced equation and our data. Let me go ahead and just show you what I'm doing. So let's see, we've got 2 copper 2 chloride plus 4 potassium iodide gives us 2 copper 1 iodide. Yeah, copper 1 iodide plus 4 potassium chloride plus what I presume to be solid iodine. And this should already be balanced for us. I find it hard to believe that they would put some balancing coefficients on some of these and leave the rest for us to balance, so I'm going to trust them this time. But no harm in checking their work. Yeah, let's check their work real quick. 2 coppers, 4 chlorines, 2 times 2. 4 chlorines here, 4 times 1. 4 potassium, 4 times 1, and still 4 potassium here, 4 times 1. 4 iodine, so 4 times 1, and 4 iodine here, 2 times 1 plus 1 times 2. Yeah, okay, it checks out. And then we've got 0.4235 moles of copper 2 chloride is reacted. 0.4235 moles of copper 2 chloride goes into the reaction. Okay, let's go ahead and set up our calculations. So we need the number of molecules of iodine. We want molecules of I2, and what else did they ask for? Grams of I2. So copper 2 chloride is your substance A and iodine is your substance B. Let's go ahead and convert. Let's go back and revisit the chart that we put together earlier, just for a quick planning session. So we start with moles of copper 2 chloride. We want to convert that to moles of solid iodine, and then we want to convert that to numbers of particles of solid iodine. So it should be a two-step sequence there, and then the other two-step sequence is to go from moles of iodine to grams of iodine instead. So we can do both of those. So first we want to get moles of iodine. So we've got, let's see, 0.42, whoops, botched that already, 0.4235 moles of copper 2 chloride. Going to convert that to moles of iodine using our balanced chemical equation. So I see that every 2 moles of copper 2 chloride gives us 1 mole of solid iodine. 1 mole of molecular iodine. And I guess I could go ahead and stop here, because from here we can branch off in 2 different ways. We can get the molecules of iodine or the grams of iodine. So if we want the molecules of iodine, then what we can do is say every 1 mole of iodine equals 6.022 times 10 to the 23 molecules. I don't think I'm going to be able to fit that. I'll just abbreviate it molec. In chemistry, we abbreviate everything. Just so you know. I mean, that's basically what the periodic table is. It's a big chart of abbreviations. So yeah, abbreviations in chemistry are very, very common. Wait till you see some of the wacky abbreviations we have. So that's for getting the molecules, just using Avogadro's number. I strongly recommend you memorize Avogadro's number, at least to 4 sig figs. You can memorize more digits of Avogadro's number if you're feeling particularly nerdy, but usually 4 sig figs is plenty. And then going on to grams, if we want to go to grams, then we can say every 1 mole of molecular iodine is equal to how many grams? Periodic table says iodine is 126.904. That's for 1 mole of atoms of iodine, but 1 mole of molecules of iodine, which contain 2 atoms each, would be twice that much. So 126.904 times 2 gives us 253.808. 253.808 grams of molecular iodine. Okay, and from there we should be able to get 2 different answers, so let's go ahead and calculate. I should probably just show my calculator so you can see the steps as I do them. So we've got 0.4235 times 1 over 2 to convert between moles of copper 2 chloride and moles of molecular iodine. And let's see, so that's an exact conversion. We should have 4 sig figs in the end because we had 4 sig figs to begin with. So 0.2118 is what I would round this to. 0.2118. That's moles of molecular iodine, and then from there we can go in either one of these directions. So let's start with particles, and I think I want to switch my calculator to scientific mode for this because I'm expecting a really big number. 0.2118 times 6.022 times 10 to the 23 particles over every 1 mole of said particles. In this case, our particles happen to be molecules. So let's see, 4 sig figs times 4 sig figs should still be 4 sig figs. So 1.275, and the 4 does not round us up, so yeah, 1.275. I guess I'll write it over here. 1.275 times 10 to the 23 molecules of iodine. Molecules of I2. Okay, that's a lot of molecules. Surprising to no one. And then for grams, I go with, and I guess I'll go back to normal mode for this. For grams, we've got 0.2118 moles of I2 times 253.808 over 1. I know doing the extra steps of pushing the divide by and 1 button might seem pointless, but I think it's good to form that habit. So that's why I do it. 53.756, the 6 would round us up, so 53.76 if we're keeping 4 sig figs. Because it was 4 sig figs versus 6 sig figs and infinite sig figs, so yeah. We should still have 4 sig figs, 53.76 grams. 53.76 grams of molecular iodine. And there you go. Those are our 2 answers to that last problem. So now we've seen examples of going between grams of A and moles of A, right? We've seen going from here to here, or sorry, between grams of A and grams of B, rather. So we've seen examples of going from here to here. We've seen now an example of going from here to here. So we've worked with Avogadro's number, we've worked with particles, we've worked with grams, we've worked with moles. We still haven't worked with liters. So now it's time to start talking about the topic of concentration. Now it's time to start talking about the topic of concentration. And I won't go too in depth here. I'll just kind of introduce a bunch of things and we'll talk about concentration in much more depth. Well, I'll talk about molar concentration in depth here, and then we'll talk about other types of concentration in some more depth when we get to another chapter that's all about concentration and solutions. So, in order to understand the concept of concentration, we first have to talk about what a solution is. A solution is something you've already seen. Solutions are another name for homogeneous mixtures. Solutions are homogeneous mixtures. It's just another name for them. So they are mixtures in which all of the particles are evenly distributed throughout one another, but those particles are mixed. They aren't reacted with each other. They're not chemically bonded to each other. So each of the different substances in the mixture still retains its own unique identity. And of course, when we think of solutions, specifically we think of those homogeneous mixtures in which water is usually a major component of the mixture. Those are what we call aqueous solutions. Aqueous solutions. So aqueous solutions are solutions in which the solvent is water. Solutions in which the solvent is water. Water. Don't know what I was trying to write back there. Solutions in which the solvent is water. And you might be asking, what on earth does solvent mean? Well, the solvent is basically the major part of a solution. So every solution has a solvent and a solute. Well, maybe not every solution. When we get into the solutions chapter, we'll talk about the question of mixing equal parts water and alcohol and determining which one, if either, is truly the solvent. But that's a question for a later time. For now, we can say the solvent is basically the stuff that you dissolve other stuff into. Solvent is the major component, typically, of a mixture. So I guess take this with a grain of salt. So I'll put it in quotes there. Major component of a solution. It's the stuff in which you dissolve other stuff, and the other stuff that you dissolve into the solvent, that's called the solute. That's called the solute. So, the substance dissolved in the solvent. You could also call it the minor component of the solution. The substance dissolved in the solvent. So, clear-cut example, if you put sugar in water, sugar is the solute and water is the solvent. If I put a drop of green food coloring in water, the green food coloring is the solute and the water is the solvent. I'm going to be using this for an experiment later. But yeah, the substance dissolved in the solvent, that's called the solute. And of course, because chemists love their abbreviations, I think you should know solutions are sometimes abbreviated SOLN. So just keep that in mind. But yeah, so these are all the different parts of a solution. the solvent plus the solute basically makes your solution. And aqueous solutions are the most common solutions we will be dealing with. So, yeah, that's good to know the definition of an aqueous solution. Usually, if you're not told otherwise, it's pretty safe to assume the solvent is water, unless you know the substance isn't really soluble in water, in which case you might need to do a little bit of digging around to find an appropriate solvent, or maybe you'll be facing a question in which the solvent doesn't matter. Anyway, so for every solution, for every mixture, you have different measures of what's called the concentration. Basically, concentration is the ratio of solute to solvent. You can think of concentration as the ratio of solute to solvent. And to give you an intuitive sense of what that means, imagine you do sugar water, for example, or let's not stick with raw sugar water, let's do something like tea. Let's say you've got tea and you've sweetened it with a little bit of sugar, but you've got the tea molecules, I guess you could call them, and the sugar molecules all mixed in there in the water, and that would be a homogeneous mixture so long as you don't have like chunks and tea leaves in there, in which case it would suddenly be heterogeneous. But you can actually get a sense of the concentration of sugar in your tea based on the sweetness. If you take one sip of tea and taste how sweet it is, and then you add some more sugar and you take another sip of tea, then you can recognize that the concentration of sugar in your tea went up for that second sip because it'll taste sweeter. I really shouldn't be talking while writing. I already had a little gaffe with that in the last video. The ratio of solute to solvent in a solution. But yeah, going back to my tea example. So you can tell when the concentration of sugar in your tea is high because it'll taste sweeter. You can tell when it's low because it'll taste more bitter. And I guess you could also tell the concentration of the tea itself. You can sense the flavor of the tea and the intensity of that flavor. So that's concentration that you can actually kind of pick up on with your tongue. Unfortunately, you can't do that with everything in chemistry. In fact, you can't do that with most things in chemistry. You can't taste nitric acid to get a sense of its concentration, so we really need something more, I guess, safe. We need something safer in order to measure concentrations. Plus, we need something more accurate. Taste testing isn't really an accurate way of measuring concentration. Another way you can get an intuitive sense of concentration is by looking at color. For solutions that actually have a color, the intensity of the color can tell you something about the concentration. In this case, the darker the greenness of my food coloring mixture, the higher the concentration. I only put 1 drop of food coloring in here, so it shouldn't be too high of a concentration, but that green is pretty clear. You can clearly see the greenness. It's not very faint. I'll try to make it fainter later on. But yeah, concentration generally is just the ratio of solute to solvent. So I guess going back to this, another way that I can get a lower concentration of green food coloring, instead of using less drops of food coloring, I could have just put in 2 drops of green food coloring and used twice as much water, and I would end up with the same concentration. So it depends not just on the solute itself, it also depends on the solvent. If we go back to our tea example, if you add water to the tea, the flavor is going to get weaker. One day they're going to make flavor into a word. I just know somebody's going to meme this into oblivion. Flavor. So yeah, concentration, it doesn't depend directly on the amount of solute nor directly on the amount of solvent, but on the ratio between them. And there are different kinds of concentrations that you can define. So one type of concentration we can define we've already seen before, which is percent mass or percent composition. We saw that in the last video. We saw, what was it? The percent mass of carbon in calcium carbonate was 12.0%. You could say that's the concentration of carbon in calcium carbonate if you wanted to. You could figure out the, if we go back to an example like sugar water, you could figure out the grams of sugar and the grams of water, and of course the grams of the whole thing, which would be the grams of the sugar plus the water, and take the grams of sugar over the grams of sugar plus water and multiply that by 100%, and that would be one measure of concentration. You could also use percent by volume, especially if you're mixing two liquids like water and alcohol. You could use percent volume. So you could add the liters or milliliters of alcohol and the liters or milliliters of water if you're mixing water and alcohol, and that would give you the total liters. And then let's say you want the percent volume of alcohol, then you would just take the liters or milliliters of alcohol over the total liters or milliliters of water plus alcohol, multiply by 100%, and there's your percent volume. You can also have grams per liter. So you could just figure out how many grams of solute you're putting in and how many liters of solution you end up with after you stir and everything, and that could be a measure of concentration you could use. We also have something called parts per million or parts per billion. Parts per million and parts per billion. These are usually gram ratios, so there'll be ratios of grams of solute to grams of solution. And usually these are useful when the grams of solute are extremely tiny compared to the grams of solution. You might see parts per million or parts per billion being used by environmental agencies that are trying to define, for example, how many parts per million or how many parts per billion of lead should be allowed in water before it becomes dangerous, right? Because even tiny amounts of lead can be really dangerous, so the amounts of lead that could be considered toxic should be on the order of parts per million, right? If you're measuring it in grams per liter or mass percent, then the numbers are probably already too dangerously big. What else do we have? We've got molarity, molality, and the mole fraction. Molarity, molality, and the mole fraction. Molarity, molality, and I guess I'll write it over here so I can have it all on one nice line, the mole fraction. Most of the time in chemistry we will be working with molarity. We will have time to look at molality and mole fractions at a later time, but molarity is the one that we want to cover for today. Molarity is a type of concentration that's specifically designed for use in stoichiometry problems, or solution stoichiometry if you want to be specific about it. Molarity uses moles of solute over liters of solution. Molality, we'll see later, uses moles of solute over kilograms of solvent, and mole fraction is something that is usually used with mixtures of gases rather than aqueous solutions, but it can also be used with aqueous solutions, of course. But yeah, we'll introduce those at a much later time. For now, let's focus on molarity. So molarity is a measure of concentration that uses moles of solute over liters of solution. And there we go. I'm using that abbreviation for solution already. Moles of solute over liters of solution, that is concentration in molarity. Let's do a couple of sample calculations for this. Let me ask, what is the molar concentration also known as molarity? So whether you hear the term molar concentration or molarity, know that they mean the same thing. What is the molar concentration or molarity? Concentration, that should be an O, of the following. Let's do A. Let's do 55.6 grams of potassium chloride in, let's do 1.37 liters of solution. And B, let's do let's do 12.0 grams of sodium bromide in, let's make it 128 milliliters of solution. And I guess I should have question marks here. I think in the last video somewhere I used a period instead of a question mark. That's why I'm not the English tutor. But you know, I'll try to be good with my grammar and spelling where I can. Speaking of spelling, I think I also misspelled judgment in the last video when I wrote use your best judgment. But those are not among the mistakes that I point out in my pinned comments. I usually use my pinned comments to point out chemistry-related mistakes. Let's see. So, of course, since molarity is defined as moles of solute over liters of solution, we need to convert our grams to moles. Okay, so potassium chloride, let me calculate that real quick. Potassium 39.098 plus chlorine was 35 point something. 35.453 is 74.551, so 55.6 grams of potassium chloride every 74.551 grams is equal to 1 mole, so that'll give us moles, and then we've got 1.37 liters. We'll save that for later. Let's also go ahead and do the sodium bromide. So 12.0 grams of sodium bromide every 1 mole is equal to, periodic table says, I remember sodium 22.990 from before, and bromine is 79.904. So that's 102.894. 102.894 grams. Okay, and let's go ahead and calculate these. So 55.6 times 1 over 74.551. Rounded to 3 sig figs, that would be 0.746. moles. And then for the sodium bromide, 12.0 times 1 over 102.894 gives me 0.117 if I round to 3 sig figs. And there we go. That gives us our moles of solute for both cases, and I see the red marker is about as good as dead, so to the trash you go. And let's grab a replacement marker for red. Let's go with navy blue. I think it's navy blue, or maybe it's gray or black. I can't quite tell. Maybe the lighting in my room is off. But yeah, so we've got our moles of solute now, and for liters of solvent, we already have that for part A, so let's go ahead and do 0.746 moles of solute over 1.37 liters of solution gives us 0.746 over 1.37, 0.545 if I round that to 3 sig figs, 0.545 moles per liter, or you could also say 0.545 molar with a capital M. So the capital M for molarity is the same as saying moles per liter. So 0.545 moles per liter or 0.545 molar is how you would pronounce that. Okay, and then for 0.117 moles, I need to divide that by the liters of solution. I've got 128 milliliters of solution, so I need to convert that to liters first. Shouldn't be too hard. It's a simple metric conversion. 128 milliliters every, let's see, every 1 liter is equal to 1,000 milliliters. So dividing by 1,000, move the decimal 3 places, it's 0.128. You probably didn't even need me to write that out, but you know, we'll gradually start skipping some of these easy steps as we move forward. But for now, I'm not going to assume anything about your skill level other than, you know, what I've already asked you to do in previous videos. You are reading the study suggestions in the descriptions, right? I sure hope so. Okay, so we've got 0.128 liters, so where were we? 0.117 moles over 0.128 liters gives us, and I probably should have written that up here too, is equal to 0.117 over 0.128 is, if we round to 3 sig figs, 0.914. 0.914 moles per liter, or 0.914 molar. Okay, and there's measuring or calculating molar concentration. We could also start with a molar concentration and use that as a conversion factor. Molar concentrations can be used as conversion factors between moles and liters, right? Ratios, like we mentioned in the last video, can also be conversion factors. So we can do moles per liter, we can use that as a conversion factor. So I could say, for example, if I have a Let's see, what question could I ask? Let's say, how many moles of nitric acid are in a let's do 2.50 liter sample of a 0.805 molar solution of nitric acid. This should be a very, very simple conversion if you know what you're doing. We start with 2.50 liters of HNO3, 2.50 liters of nitric acid, and then the molarity tells me that for every 1 liter of nitric acid solution, every 1 liter of solution contains 0.805 moles of nitric acid. And of course, I did not leave enough space here. Should have made my parentheses wider. So let's scribble that out. Every 0.805 moles of HNO3 are contained within 1 liter of solution. And that's it. We can calculate the moles of solute that we have in here. So 2.50 times 0.805 over exactly 1. So the 1 here does not affect the number of sig figs. 2.50 times 0.805 and round to 3 sig figs. 2.50 times 0.805 over 1 is 2.0125. We need to round that to 3 sig figs, so 2.01 moles of nitric acid. Oh, and if I can get moles of nitric acid, and I had a reaction involving nitric acid, I could get moles of some of the other substances in that reaction, and then I could get the grams or the numbers of particles. Ooh, now we finally have the key to address the upper left and upper right corners of our I don't even know what to call this thing, the stoichiometry flowchart, let's call it. Now we can finally have at least one of the two methods of converting between liters and moles of substances. The other method, like I mentioned before, will be covered when we cover gas laws when we get to like 2 or 3 parts from now. Let me think. So this part, I already know what I'm going to be doing next part, and yeah, gas laws will be after next part. Gas laws will be after the next part. Okay, so let's go ahead and turn to some more questions that we can do. Let's go ahead and look at some more questions that we can do now that we know a little bit about concentration. So we've got problem 46 here, says hydrogen gas is produced by the reaction of 118.5 milliliters of a 0.8775 molar solution of phosphoric acid according to the following equation. 2 atoms of chromium metal, or 2 moles of chromium metal I should say, reacts with 2 moles of phosphoric acid to produce 3 moles of hydrogen gas and 2 moles of chromium phosphate. Outline the steps necessary to determine the number of moles and mass of H2 and perform the calculations outlined. Okay, so same shtick as before, so they want you to really focus on the steps first. Which again, if you're already good with the calculation part, if you're already competent at plugging in numbers, then you shouldn't waste time practicing that part. You should practice the hard part. You should practice the part that you're not so good at yet. Let's see. So I'm going to go ahead and copy this down. So we've got 2 chromium and 2 phosphoric acid. And that produces H2, or 3 moles of H2 rather, and 2 moles of chromium phosphate. Okay, good to go. And we were told that we've got 118.5 milliliters of this stuff. 118.5 milliliters of this solution is 0.8775 molar. Okay, and they want us to figure out the moles and grams of hydrogen. I'll just go straight to the grams. Moles can be calculated along the way anyway, so we want grams of H2. I'm not going to worry about moles. We've already seen plenty of examples of that. Okay, let's see. So we have a number of extra steps here. First of all, we need to convert just one extra step really, which is needing to convert milliliters to liters. That's just going to be a metric conversion. And converting milliliters to liters, if a liter is 1,000 milliliters, then it shouldn't be too hard. Just move the decimal place. But yeah, so every 1,000 milliliters is equal to 1 liter. So that'll cancel out milliliters and give us liters of H3PO4 phosphoric acid. Then we can go from liters of phosphoric acid to moles of phosphoric acid. So every 1 liter of phosphoric acid solution is 0.8775 moles of phosphoric acid. Then we're going to be switching between phosphoric acid and hydrogen gas. So every, 2 moles of phosphoric acid gives us 3 moles of hydrogen gas. So 2 moles of phosphoric acid gives us 3 moles of hydrogen gas. And now that we have moles of hydrogen gas, we can get grams of hydrogen gas. Every 1 mole of hydrogen gas is how many grams? Remember, that's molecular hydrogen. You've got 2 atoms there, so whatever you get on the periodic table for hydrogen, 1.008, we're going to multiply that by 2. 2.016 grams of hydrogen. And I realize I did not write H3PO4 everywhere here, but I guess I'm kind of glad I didn't, because it saved some space and made sure I didn't have to continue writing on another line. And it always looks nicer when you do it that way. So let me see. I'll just go ahead and go through the calculations then. So 0.1185 is what you get when you convert to liters. So 0.1185 times 0.8775, 4 sig figs, so that's going to round to 0.1040. 0.1040 once you get here, 0.1040 moles of phosphoric acid. Okay, and then multiply that by 3/2. That's an exact conversion, so we should still end up with 4 sig figs in the end. 0.1040 times 3/2 is 0.156 according to my calculator, but we need 4 sig figs, so it should be 0.1560 moles of hydrogen gas. And then if we convert that to grams, multiply by 2.016/1, and rounding to 4 sig figs gives me 0.3145. 0.3145 grams of hydrogen gas. And there's our final answer. Okay, should we do another one? Yeah, let's go ahead and do this other one. So it says gallium chloride is formed by the reaction of 2.6 liters of a 1.44 molar solution of hydrochloric acid according to the following equation. 2 gallium metal plus 6 hydrochloric acid gives you 2 gallium chloride plus 3 hydrogen. Gallium, I believe, is below aluminum. Yes, it is. So it's in that +3 block of the periodic table, or a +3 column, rather, of the periodic table. Okay, good to know. So, yeah, GaCl3 does seem to be the correct formula for gallium chloride. Okay, let me go ahead and copy the information from that, and let's do some more stoichiometry. So we have 2 gallium plus 6 hydrochloric acid yields 2 gallium chloride and 3 hydrogen gas. And what do we want from here? They said outline the steps necessary to determine the number of moles and mass of gallium chloride. We'll just skip the moles and figure out the grams of gallium chloride that we get. And the starting amounts they gave us were 2.6 liters of 1.44 molar HCl. So we've got 2.6 liters of this stuff and a concentration of 1.44 molar, or moles per liter. So 2.6 liters of solution with a concentration of 1.44 molar in HCl. Okay, let's go ahead and set this up. Shouldn't take too long. So we start with our 2.6 liters of HCl solution, and we know from the molarity that for every 1 liter of HCl we get 1.44 moles of HCl. Once we've got moles of HCl, we can go to moles of gallium chloride. So every 6 moles of HCl gives us 2 moles of gallium chloride, GaCl3. And then from there we can go from moles of gallium chloride to grams. Every 1 mole of gallium chloride equals how many grams? Okay, so gallium, according to my periodic table, is 69.732. So I have one of those plus 3 chlorines. Each chlorine is 35.453. I always forget that last digit. And if we add all those up, we get 176.091 grams of gallium chloride. Okay, and if we go ahead and perform the calculation, then let's see, 2.6 times 1.44 over 1, so 2 sig figs times 3 sig figs over infinite sig figs, 2 sig figs. So that'll give us 3.7 moles of HCl. And then 3.7 times 2 over 6. That should still have 2 sig figs, so we're going to round that to 1.2 moles of gallium chloride. And then multiply that by 176.091. 1.2 times 176.091 over 1. And that should still round to 2 sig figs, so we've got 211.309. I'm going to round that to 210 grams of gallium chloride. And to make it extra clear that it's 2 sig figs and not 3, I would write it as 2.1 times 10 to the 1 grams of gallium chloride. Your teacher probably won't appreciate you taking the extra step to do this. Your teacher probably won't care and will settle for you writing 210 grams, but you know, if you care more than your teacher, then that's something to be proud of. Let me see here. There was something I wanted to mention. Oh, right. So some students might ask, while I was calculating the molecular mass of, or formula mass of gallium chloride. Some might ask, when you multiply the chlorine by 3 when calculating the molar mass, if you do that, you get 3 times 35.453 is 106.359. So you went from 5 sig figs to 6 sig figs. So some people might say, when I do 3 times 35.453 for the chlorine, and that gets me 106.359, you might say that I have to round this to 106.36 because I just multiplied infinite sig figs by 5 sig figs. I should get 5 sig figs, right? Well, not in this case, because the multiplication that's going on here is really just a shortcut for addition. What you're really doing is you're adding 35.543 plus 35.4... Did I say that right the first time? 35.453 plus 35.453 plus 35.453. So under addition and subtraction, the rule is you go with least decimals, and since they all have 3 decimals, you can still end up with 3 decimals in the end. So in this case, no, you do not need to round it to 106.36. I know probably most of you don't care about that, but some people do care, so I just wanted to point it out for the people who do care. You can get away with this because the multiplication here is really just serving as a substitute for addition. Okay, let me see. What do I want to do next? I think now is time to talk about density, and then we can look at some of the, as I like to call them, hardcore stoichiometry problems. They're probably not that hard, it's just they require a little bit more thinking than the usual stoichiometry problem. So let's talk density real quick. What is density? Density is kind of similar to concentration. Density is the ratio of mass to volume. At least that's what we usually mean when we say density, but in fact there are different kinds of density. Specifically, we're talking about volume mass density. Specifically, when we say density in chemistry, we almost always mean volume mass density. If you're taking physics, then you probably learned about other types of density. You might learn about charge density instead of mass density, so like coulombs of charge per, I don't know, cubic meters of charged object or something like that. And of course, density doesn't always have to be based on volume. Sometimes you can distribute something over a mass. So if I spread peanut butter on a piece of toast, then I could take the grams of peanut butter I spread on the toast divided by the area of that piece of toast in square inches or whatever, and I could get the grams of peanut butter per square inch of toast that I spread on my bread. Or whatever it is you do with your peanut butter. But in chemistry, when we say density, we almost always mean volume mass density. In fact, I can't think of an example where I've ever seen chemistry use anything other than volume mass density. But just know there are other types of density out there. There's linear density, also known as length density, where it's the grams per meter or grams per centimeter, or even the charge per meter or centimeter if you're talking charge density. In math and statistics, there's something called probability density, which is not the most intuitive thing to explain, so I'm not going to bother trying to explain what it is. Although we will kind of mention probability density a little bit when we talk about electronic structure, so maybe we will have to talk about it after all. But we'll talk about it when we need to and if we need to. Anyway, density is the ratio of mass to volume. Oftentimes in chemistry, density is given in grams per liter. You might recall that grams per liter is also one of the measures of concentration I mentioned earlier. So don't confuse the two. Grams per liter as a concentration is grams of solute over liters of solution, while grams per liter as a density is grams of the substance over liters of the same substance. But yeah, once you're given a density, then you can easily convert between grams of that thing and liters of that thing. In fact, let's go ahead and put that into our little flowchart from before. Oh my goodness, how many pages have I used so far? How many trees have to die for my satisfaction? Let's go ahead and do this and this. So you can go between grams of a substance and liters of that same substance if you have the density. Let's go back to peach since that's the color scheme I was using. You can use density to interconvert between grams of a substance and liters of that same substance, or vice versa. So there you go. I think that completes our flowchart. So I don't know, you might want to take a screenshot of this or make a copy of it for yourself, or do whatever, and if you're feeling particularly artistic, maybe, I don't know, slap something together in Photoshop and share it with your friends, or keep it to yourself. Whatever you want to do. But yeah, density is just a ratio. We use it like other ratios in our calculations as conversion factors. So that's what we're going to do. It's really not that hard to make use of density, though I do want to talk a little bit about density intuition before we move on to using it. So when something has high density, I can think of something with high density like gold. Gold has a really high density. So if I had a block of iron and a block of gold, if gold has a higher density, that means there's more grams in 1 liter of gold than there is in 1 liter of iron. So if I had 2 equal volume blocks, but one was gold and one was iron, the block of gold would weigh more. It would be heavier despite having the same size as the block of iron. So hopefully that gives you a little bit of a sense of what density is. I could also say if I have equal grams of gold and equal grams of iron, if I had, for example, 10 grams of each, 10 grams of gold would look much smaller because gold has a higher density. You don't need as big of a piece of gold to weigh the same as an equal piece of iron in terms of mass. But yeah, that's some density intuition for you. If you need more density intuition, then I guess look up another video on YouTube that talks about density. But as far as chemistry is concerned, we're only going to use density for our calculations, so as long as you know how to use it in calculations, you should be fine. Let me see. So yeah, let's switch over to these questions over here. And some of these can be pretty hardcore. I don't know whether or not I want to do all of them, but we'll see. 52 says, automotive airbags inflate when a sample of sodium azide is very rapidly decomposed. So you've got 2 moles of sodium azide in the solid form, that's what that S stands for, gives you 2 moles of solid sodium metal and 3 moles of diatomic nitrogen gas. And I guess they wanted to emphasize that the nitrogen was a gas, so you would understand it's the nitrogen that fills up the airbags in your car when you crash into another vehicle or into a tree or whatever. But yeah, it's asking what mass of sodium azide is required to produce 2.6 cubic feet or 73.6 liters of nitrogen gas with a density of 1.25 grams per liter. Thankfully, they gave it in grams per liter and they gave us liters. Sometimes they give you grams per milliliter and you can still work with that. That's perfectly fine. But grams per liter is what we have in this problem, so that's what we're going to use. So let me go ahead and copy down the information. We've got 2 sodium azide plus, or no, not plus, just directly decomposes. It's a decomposition reaction. So we've got 2 sodium azide gives us 2 sodium plus 3 nitrogen gas. And they gave us 73.6 liters of nitrogen gas is what we need to produce. And they gave us the density as 1.25 grams per liter. And they're asking how much sodium azide should we have in this car so that it can inflate an airbag up to a volume of 73.6 liters. So we want grams of sodium azide. Okay, so in this case, these liters are not liters of a solution, so I can't go from liters to moles directly like I could with molarity, so in fact I have to go from liters to grams of nitrogen, and then once I do that, I can go from grams of nitrogen to moles of nitrogen, and then moles of nitrogen to moles of sodium azide, and moles of sodium azide to grams of sodium azide. So let's go ahead and set that up. So we've got 73.6 liters of nitrogen gas. And for every 1 liter of nitrogen gas, we've got 1.25 grams of nitrogen. Or nitrogen gas, to be specific, N2. Let's see. Then we've got, I can go from grams of N2 to moles of N2. So every 1 mole of nitrogen gas is equal to how many grams of nitrogen gas? Periodic table says nitrogen is 14.007. Multiply that by 2 because you've got 2 moles of nitrogen atoms in every 1 mole of nitrogen molecules, and that gives us 28.014. It was 7, right? Yeah, okay. Just double checking my mental math. Then we can go from moles of nitrogen to moles of sodium azide. So every 3 moles of molecular nitrogen gives us 2 moles of sodium azide. And finally, we can go from moles of sodium azide to grams. Every 1 mole of sodium azide is equal to how many grams of sodium azide? I really botched this. Let's see. So sodium 22.990 plus 3 times the nitrogen, which was 14.007, gives us 65.011. 65.011 grams of sodium azide. Okay, and now we can just calculate. So 73.6 times 1.25 over 1, rounding to 3 sig figs, that's 92.0 grams of nitrogen. Then multiply that by 1 over 28.014. We still have 3 sig figs, so that's going to be 3.28 moles of N2. Then we can convert that to moles of sodium azide, multiplying by 2 over 3. That's an exact conversion, so we should still have 3 sig figs, 2.19 moles of sodium azide. And then 2.19 times 65.011 gives us 142.37, rounding to 3 sig figs. That should be 142. 142 grams of sodium azide would be needed to fill that airbag. I just realized there was something I forgot to mention when talking about solutions, so maybe we should take a quick detour and talk about that real quick. So, something I forgot to mention when talking about solutions was the concept of diluting a solution. Dilution. So, sometimes when you're given a solution of a given concentration, the concentration might be too high. You might want to water it down, so to speak, so that you can get a lower concentration that's easier to work with, or just more appropriate for your needs. Concentration can affect all sorts of things, like how quickly a reaction goes, something we will learn about in more detail in a much later chapter. But yeah, sometimes the need arises to lower the concentration of a solution you already have. Suppose I have a really dangerous concentrated 8.0 molar solution of nitric acid. Suppose I have an 8.0 molar nitric acid solution. That's got a lot of nitric acid in there. And suppose I want to bring it down and make it a 1 molar nitric acid solution. What do? Suppose I've got, let's suppose I have, I don't know, 2.4 liters of this 8 molar nitric acid solution, and I want to create a, let's say I want to create a 0.50 molar nitric acid solution. Well, I don't think it's counterintuitive to believe that you can achieve that by simply watering it down. So basically, by doing this. Remember, I prepared this, if you're willing to believe me, by just adding 1 drop of green food coloring, and it looks like, according to my beaker, I've got about 75 milliliters in here. So if I add some more water, I'm going to try and get it to 150, for example. Okay, so I got this from 75 milliliters to 150 milliliters, and apparently when I did this last time, the camera angle didn't really help you see the color getting lighter. I don't know if it worked better this time. I guess I'm going to have to wait until I see the final video to confirm the results. But if you're willing to believe what I see from my angle, the color did get a little bit lighter. In fact, it should be about half as light. So, 2 things have changed, and 1 thing still hasn't changed. The 2 things that changed were the volume of this solution, it's now doubled, and the concentration of the solution, it's now half. But the 1 thing that didn't change is the fact that there is still 1 drop of food coloring in there. I didn't remove any food coloring, I didn't add any food coloring, I just added more water, so the total amount of solute inside there should still be the same. The amount of solute is constant, and we can take advantage of that fact to get the dilution equation. The dilution equation says molarity before times volume before equals molarity after times volume after. Molarity before times volume before equals molarity after times volume after. Why is that? What is the molarity times the volume? Well, molarity before times volume before equals the moles of solute. So in the case of this problem here, if I did 2.4 liters, if I did 2.4 liters of nitric acid solution times, we've got for every 1 liter 8.0 moles of nitric acid, then that gives us 2.4 times 8 over 1 is 19.2, which I would round to 19. We've got 19 moles of nitric acid in there. And if I water it down, there should still be 19 moles of nitric acid in there. So whatever the new concentration is, and I guess in this case the new concentration, I want it to be 0.50 molar. So if I've got 0.50 moles of nitric acid for every 1 liter of my new solution, and I multiply that by the volume V2, however many liters it is, I should still get 19 moles of nitric acid. I should still get 19 moles. So volume 1 times molarity 1 equals volume 2 times molarity 2 equals 19 moles either way. So M1V1 equals M2V2. So in this case, if we're trying to get an 8 molar solution, dilute it down to a 0.5 molar solution, then I guess my question is, how many liters of water should we add? Let's go ahead and calculate using the dilution equation. We've got 8.0 times 2.4 is equal to 0.50 times V2. Doing a little bit of algebra, just divide by 0.50, and what we get is 8.0 times 2.4, we already did, is 19.2, round to 19, divided by 0.5 should be 38. So V2 equals 38 liters. Some people will make the mistake of circling this as their final answer. Sometimes this is the final answer, other times it's not. My question was, how much water should you add in order to dilute this solution down from 8 molar to 0.50 molar? 38 liters is what the final volume should be. It's not how many liters you add. To get how many liters you add, you would have to subtract 38 minus 2.4, the final volume minus the original volume, and it looks like you would have to add about 36 liters of water. So in this case, it does seem kind of clunky. 38 minus 2.4 is going to be 35.6 if I'm not mistaken. 38 minus 2.4, yeah, 35.6, which you have to round up to 36 because of the decimal rule. No decimals, 1 decimal you round to no decimals. So yeah, you would have to add 36 liters of water here. And of course that feels kind of clunky and imprecise. Feels like you should be adding 35.6 liters anyway. But, you know, that just goes to show you that for a problem like this, you probably should have started with more sig figs to begin with so that you wouldn't have this problem. Anyway, that's dilution, and that's just a quick example of it. Dilution is really, really easy to do, so I don't think we need any more examples than that. Let's go back to our so-called hardcore questions and see what else we can do here. So next up we have, should we do the one with urea? Urea is manufactured on a large scale for use in producing urea formaldehyde plastics and as a fertilizer. What is the maximum mass of urea that can be manufactured from the carbon dioxide produced by combustion of 1 times 10 to the 3 kilograms of carbon followed by the reaction? Let's see. So I'm going to need to read this a second time. What's the maximum mass of urea that can be manufactured from the carbon dioxide produced by combustion? Oh, okay, this one's pretty elaborate. So this requires a lot of out-of-the-box thinking. So yeah, let's go ahead and do it. So we need to figure out how much urea can be formed from the carbon dioxide that is given, and we don't have the reaction for manufacturing urea. We just know that we're going to get the carbon for the urea from carbon dioxide. So this one's going to require a little bit of out-of-the-box, well, a lot of out-of-the-box thinking. Okay, let me go ahead and copy down all the data. So we've got urea, which is CO, where did it go? NH2. This would be some type of diamine in organic chemistry nomenclature, which you haven't learned yet. And we've got the reaction, carbon dioxide. Oh, wait, never mind. We do have... Hold on, am I misreading this problem? Oh, okay. They gave us the reaction for forming urea. Never mind, you don't need that much out-of-the-box thinking after all. But it's still worth doing. So we've got carbon dioxide, 2NH3. So that gives us urea plus water. That gives us urea plus water. And I forgot my balancing coefficients, didn't I? Oh, no I didn't. There's only one balancing coefficient. Okay. Good to know. And they said, what's the maximum mass of urea that can be manufactured from the carbon dioxide produced by combustion of 1,000 kilograms of carbon? So the other thing that they tell us is we've got the combustion of 1,000 kilograms of carbon. Combustion reactions, as you know, are reactions between hydrocarbons and oxygen usually, but I also said that sometimes combustion is referred to as just anything that reacts with oxygen, which is the meaning that they're using here. In this case, they're just having raw carbon reacting with pure oxygen, and that'll form carbon dioxide. And that's actually balanced, conveniently for us. 1 carbon, 2 oxygen, 2 oxygen. That's perfect. Okay, so they start us off with 1,000 kilograms of carbon, 1.00 times 10 to the 3 kilograms of carbon. And then from there, we're going to need to calculate the amount of carbon dioxide we have, and we can use that carbon dioxide up here to figure out the amount of urea produced, and then we can calculate the mass of urea that can actually be produced. Alright, let's just get straight to it. So converting kilograms to grams, 1.00 times 10 to the 3 kilograms of carbon. Every 1 kilogram is 1,000 grams. So that gives us, well, I'll just save the calculations for later. And then we can convert from grams of carbon to moles of carbon. Every 12.011 grams of carbon is 1 mole of carbon. And then, of course, every 1 mole of carbon, according to our second reaction, every 1 mole of carbon can give us 1 mole of carbon dioxide. I missed the L. 1 mole of carbon dioxide, CO2. And then, of course, every 1 mole of carbon dioxide, according to the first reaction we have in the top, every 1 mole of carbon dioxide will give us 1 mole of urea, CuNH2. And then we can calculate the molar mass of urea. So let's see, every 1 mole of urea will give us how many grams of urea? Oh, and I guess I forgot to write carbon here and here. Okay, let's figure out the molar mass of urea. So carbon is in there, so 12.011 plus 1 oxygen, 15.999, plus we've got 2 nitrogens and 4 hydrogens since it's NH2 by 2. So 2 nitrogens, that would be 2 times 14.007 plus 4 hydrogens, that's 4 times 1.008, and that gives us a total of 60.056. 60.056 grams of urea per mole of urea. Okay, that wasn't too bad. It just took a bit to set it up, but the calculation part is easy. So I think we're going to skip the calculation part since we got the important part out of the way. Let's go ahead and move on to number 54. 54 says, in an accident... Oh, let me show it to you. So 54 says, in an accident, a solution containing 2.5 kilograms of nitric acid was spilled. 2 kilograms of sodium carbonate was quickly spread on the area, and carbon dioxide was released by the reaction. Was sufficient sodium carbonate used to neutralize all of the acid? This one we'll probably want to go back to after we learn more about acids and bases, so yeah, let's skip this one. I see what they're getting at, but we haven't talked about acid-base reactions yet, so we'll skip it for now. 55 is a rather interesting one. A compact car gets 37.5 miles per gallon on the highway. If gasoline contains 84.2% carbon by mass and has a density of 0.8205 grams per milliliter, determine the mass of carbon dioxide produced during a 500-mile trip. And we've got 3.785 liters equals 1 gallon is the conversion factor they want us to use here. So I guess we don't have to use my table from last time for that. Okay, let's go ahead and try to set that up. It requires some out-of-the-box thinking. Again, it's not your typical stoichiometry problem. It's probably not the kind of problem your teacher will ask you, but it's important to be able to do this, because if you can handle this, you can handle anything. So, compact car, we've got 37.5 miles per gallon. We get 37.5 miles per gallon. That's going to be important later. We have gasoline is 84.2% carbon by mass. So 84.2% carbon in gasoline. And we've got gasoline has a density, so gasoline density is 0.8205 grams of gasoline per milliliter. And it says determine the mass of carbon dioxide during a 500-mile trip. So we've got 500 miles. I'm going to assume that's 3 sig figs and not just 1 sig fig. Otherwise, this would be a problem that is rife with imprecision. So I'm going to treat it as 3 sig figs. I'm going to count the 2 zeros. This is what I meant in the last video when I said use your best judgment. And finally, they gave us the conversion between liters and gallons, 3.785 liters equals 1 gallon. Okay, so that's all the data that they gave us. Let me double check. And of course what they want is the mass of carbon dioxide produced. So want grams of carbon dioxide produced. Grams of CO2 produced. Okay, so in this case they didn't really tell us the structure of gasoline, but you can assume it's some sort of hydrocarbon. Or in fact, you don't even need to worry about that. Any carbon dioxide you make has to use the carbon that's in the gasoline. It's not going to get the carbon from anywhere else. So I guess we could just use the same reaction we did in the previous problem. Just raw carbon with oxygen producing CO2. So yeah, that's what I'll do. I'll just say carbon plus O2 gives you CO2. It does require a little bit of thinking to come up with this, but if you can master that sort of thinking, you'll do really well in chemistry. So carbon plus oxygen gives us CO2, and this is already balanced, so we're good to go on that front. Let's just go ahead and start setting up our calculation and see where it takes us. So we've got 500 miles to start with. That's our starting quantity. That's the only thing I have in here that's not really a ratio. And let's just go ahead and figure out how much gasoline we need, and then from there we can figure out how much carbon is in it, and therefore how much carbon dioxide is produced. So a 500-mile trip, I see I can convert between miles and gallons. So we've got every 37.5 miles equals exactly 1 gallon. Then we can go from gallons to liters. I see every exactly 1 gallon is equal to 3.785 liters of gasoline. And then every liter of gasoline, well, there is a conversion between volume and grams of gasoline, which is the density of gasoline, but that's per milliliter, so I'm going to need to convert my liters to milliliters first. Every 1 liter is 1,000 milliliters, or alternatively you could say every 1 milliliter is 1/1000th of a liter. Either way, you should end up with the same result, mathematically speaking. Let's see, what else do I want to do? So now I'm in milliliters, which means I can finally use the density of gasoline. Every 1 milliliter of gasoline gives me 0.8205 grams. And then from grams of gasoline, I can get the grams of carbon in that gasoline. So the 84.2% carbon is essentially saying that for every 100 grams of gasoline, I've got 84.2 grams of carbon. And I don't even know if that still fits on the screen. Yes, you can still see it. So 84.2% carbon in gasoline, you can just write that as 84.2 grams of carbon for every 100 grams of gasoline. And of course I'm going to take 100 to have 3 sig figs so that I don't lose any unnecessarily. And then finally you can go from grams of carbon to the stoichiometry part of it, so let's do that in another color. So once I've got my grams of carbon, I can go for every 12.011 grams of carbon, I get 1 mole of carbon. And then, according to my equation, every 1 mole of carbon can form 1 mole of carbon dioxide molecules. And every 1 mole of carbon dioxide has a molar mass of approximately 44. Let me calculate it more precisely. So it's approximately 44, but 12.011 plus 2 times oxygen is 15.999, so that's 44.009. 44.009. And given that we're going to be rounding to, it looks like 3 sig figs in the end, I guess the 0.009 doesn't matter all that much, but there it is. And now we can figure out how much pollution we've caused. Lots of pollution going on today between all the trees I'm killing with the paper I'm using and all the gasoline that's being burned by this one car. Let's just go ahead and calculate. So 500 times 1 over 3, or 37.5 gives us 13.3 if I round to 3 sig figs. So that's 13.3 gallons of gasoline used. Multiply by 3.785. So 13.3 times 3.785 is about 50.3 liters. When converted to milliliters, that's going to be 50,300 milliliters. Those last 2 zeros don't count as sig figs, of course. So maybe it would be better to write this as 50.3 times 10 to the 3 instead. So that's an alternative way of writing it. 0.8205 grams per milliliter, so 50,300 times 0.8205 gives me 41,300 if I round it. 41,300 grams, or again, you could write it as 41.3 times 10 to the 3, or 4.13 times 10 to the 4 if you prefer. I guess that would be proper scientific notation. Multiply that by 84.2, so 41,300 times 84.2 over 100, also known as 0.842, gives me 34,800. 34,800 grams of carbon, and that would also be 34.8 times 10 to the 3 if you prefer. Multiply this by, or divide it by 12.011, so 34,800 divided by 12.011 is 2,897, so I'd round that to 2,900. 2,900 moles with 3 sig figs, so this one is better off being written as 2.90 times 10 to the 3. You could also call it 2.9 kilomoles. And yeah, 1 to 1, so that doesn't change anything. And then over here, multiply by 44.009, so 2,900 times 44.009 over 1. And that gives us our final answer when rounded to 3 sig figs is 128,000 grams of carbon dioxide sent into the atmosphere, also known as 128 times 10 to the 3 grams of CO2, or probably more reasonably 128 kilograms of CO2. 128 kilograms of CO2 from a 500-mile trip. right. Let's see here. So, what else do I want to cover here? Do I have anything in here that might be worth looking at? I see this other set of problems, but I don't quite remember why I wanted it in the first place. I guess we could pick out one or two of these to wrap up our hardcore problems. Let's see, what volume of hydrochloric acid can be prepared by the reaction with excess sulfuric acid? Yeah, I guess these are more solution stoichiometry examples that we could do. Let me see, what are the other solution stoichiometry problems we've done? I don't think we did too many of those. Yeah, we only did like a couple of them. Okay, let's take a look at another solution stoichiometry problem. And I see 58 and 59 are pretty interesting problems as well. But I don't want to make this video ridiculously long. Oh, who am I kidding? It's definitely going to be really long. So maybe I might as well do all these problems anyway. What to do, what to do. Okay, let's do 57 and 59. Instead of doing all of them, let's just do 57 and 59. So for 57, it says, what volume of a 0.2089 molar potassium iodide solution contains enough potassium iodide to react exactly with the copper 2 nitrate in 43.88 milliliters of a 0.3842 molar solution of copper 2 nitrate. And they gave us the balanced equation, which is pretty common. So let's go ahead and set that up. Copy down the information as always. So we've got, first I'll start with the reaction. So 2 copper nitrate reacts with 4 potassium iodide, yielding, wait, didn't we do this one before? Oh, we did the same reaction, but the last time we did, no, it's not the same reaction. It's very, very similar though. This also produces diatomic iodine. How interesting. Plus 4 KNO3, or potassium nitrate, in other words. Okay, so it produces copper 1 iodide, diatomic iodine, and potassium nitrate. How interesting. Maybe if I spent less time marveling over some of these reactions, we'd be able to make these videos shorter. Given data, we know that the potassium iodide is 0.2089 molar, and we know the copper 2 nitrate is 0.3842 molar. 0.3842 molar. And we also know that we've got 43.88 milliliters of the potassium nitrate solution. So we need to figure out then how much, it said what volume of the potassium iodide solution is needed to react with all of the potassium 2 nitrate. Okay, so we want volume can be given in milliliters or liters. So I guess we can say liters or milliliters of potassium iodide solution. It might make more sense to convert it to milliliters in the end if it turns out to be a small number, but if they don't specify which units, then you're fine with whatever you pick. So I think I'll just stop at liters no matter what. But you're free to convert your answer to milliliters if you feel it's more appropriate. So let's see, we've got 43.88 milliliters of your copper 2 nitrate. We can convert that to liters pretty easily. 1,000 milliliters in a liter. Then we can use the molarity of the copper 2 nitrate, which tells us that for every 1 liter of the copper 2 nitrate solution, we've got 0.3842 moles of copper 2 nitrate. Okay, and then we know for every 2 moles of copper 2 nitrate, we have 4 moles of potassium iodide. 4 moles of potassium iodide. And once we have our moles of potassium iodide, this time we want a volume, so we're going to convert using the molarity. Every 0.2089 moles of potassium iodide is equal to 1 liter of potassium iodide solution. And there we go. That's the setup. And I think I'll skip the calculation to save time. Okay, we've set it up, so the calculation shouldn't take too much effort from here. Let's go ahead and look at the next one. So next I want to look at number 59. So it says the toxic pigment called white lead, Pb3OH2CO3-2. So this is one of the first times I encounter an ionic compound that has 2 different anions to 1 cation. Not really sure how I would name this, but if I had to guess, we would probably need to use prefixes to give the numbers of each of the anions. Yeah, I don't think we could get away with not stating it, because knowing the ionic charge wouldn't be enough. If I called this lead 2 hydroxide carbonate, I could see one of the hydroxide carbonates of lead having 4 hydroxides and 1 carbonate and still have 3 lead ions in it. So yeah, you definitely need numbers. So if I had to make up a rule on the spot, I would call this lead 2 dihydroxide dicarbonate, or bihydroxide bicarbonate, depending on how you want to go about it. But if you want the official naming rule for something like this, what you would really have to do is go to the International Union of Pure and Applied Chemistry. If you go to their website, and specifically if you look for their color books, I think this would be covered in the red book. You don't need to know how to name that compound for a general chemistry course, but if you're curious, just Google, you can abbreviate it IUPAC for the International Union of Pure and Applied Chemistry, or IUPAC if you prefer. Just Google IUPAC color books, and they'll have all the different books, the gold book, the white book, the orange book, the green book. And for nomenclature, you have the red book for inorganic nomenclature, and then for organic chemistry, you have the blue book. So yeah, have fun reading all 400-ish pages of the red book if you care so much about properly naming that compound, but for now, I'm just going to call it lead 2 dihydroxide dicarbonate. Let's see. So anyway, it's been replaced in white paints by rutile, or maybe it's pronounced rutil, which is just titanium 4 oxide. How much rutil in grams can be prepared from 379 grams of an ore that contains 88.3% ilmenite, which is another odd compound I see. This one has 2 cations and 1 anion, so I guess I would call this iron 2 titanium 4 oxide? Yeah, that works out, because if iron has a charge of 2 and titanium a charge of 4, then the 3 oxides with a total charge of -6 should balance that out. Okay, so yeah, FeTiO3. If it's 88.3% ilmenite by mass, then how much rutil can be prepared from 379 grams? So I guess we don't really care about the white lead at all in this problem. Okay, let's go ahead and copy down the relevant information. And I guess I'll do this on a new sheet. So we've got the reaction 2 of the iron 2 titanium 4 oxide, as I will be casually calling it, plus 4HCl plus Cl2 gives us 2 iron 3 chloride plus 2 titanium 4 oxide plus 2 water plus 2 H2O. Okay, and we are given 379 grams of an ore that contains 88.3% ilmenite. So we have 379 grams of 88.3% ilmenite. And we want to figure out how much rutil, that's the TiO2, that can be made in grams. Okay, so want grams of TiO2. Grams of titanium 4 oxide. Alrighty, let's just get straight to it. This isn't too bad. So 379 grams of 88.3% of ilmenite, we can just we could either use the equation for percent composition from before, or we can use the percent composition as a ratio and a conversion factor, and that's what I'm gonna do. It'll be quicker that way. 379 grams of ilmenite ore, so yeah, I'll just call it ore. Multiply it by, for every 100 grams of ore, we've got 88.3 grams of ilmenite. And then for well, I guess now we need the molar mass of ilmenite to convert to moles, so let me calculate that real quick. According to my periodic table, we've got 55.933 for iron, 55.933, plus for titanium we've got 47.88, oh, 2 decimals. Plus, we've got 3 oxygens, each bringing in 15.999. And I need to round that to 2 decimals, and it already is 2 decimals. 151.81. 151.81. Whoops, wrong place. 151.81 grams of ilmenite equals 1 mole. So scratch this. Equals 1 mole of ilmenite. Okay, and then we can carry on with the mole ratio that we get from our balanced equation. For every 2 moles of ilmenite, we get 2 moles of rutile. So I guess we can skip this one because it's just going to reduce to a 1 and not change anything. 2 moles of rutile, also known as titanium 4 oxide. And then we can calculate the grams of titanium 4 oxide. So every 1 mole of titanium 4 oxide is equal to, titanium was 47.88 plus 2 oxygens at 15.999 each is going to be 79.878, but because titanium only gave us 2 decimal places, we round to 2 decimal places, so that's 79.88 grams of TiO2. And there's the setup. The rest is just plug and chug into your calculator. I think you've seen me do this enough times that you now know what to do. Some of you may have already known what to do before this video even started because you actually practiced with your sig fig rules and all that from the last video and really mastered the skill. Okay, that takes care of some basic stoichiometry, but we're not quite done with stoichiometry yet. So far, we have been looking at stoichiometry through rose-colored glasses. We've been kind of unrealistic about the calculations we've been doing because we've always been assuming that we have enough of the other reactants or products to not worry about. But sometimes you do need to account for everything that you have available. So here comes the case of limiting versus excess reactants. Here comes the case of limiting versus excess reactants, and also percent yield. Limiting versus excess reactants. Let's start with that. Okay. So, a typical situation that you might encounter in the kitchen might look something like this. You know that to make a cheese sandwich you need 2 slices of bread and 1 slice of cheese. And you might go and look at how many slices of bread you have and how many slices of cheese, and you almost never have the right number of slices of each to have no leftovers. So in the example that you see in front of you on the screen, we have 28 slices of bread and 11 slices of cheese, and of course, even though you could make 14 sandwiches with 28 slices of bread, since you only have 11 slices of cheese, you can't make 14, you can only make 11, and then you're going to have some leftover bread. So this intuition shouldn't be too foreign to you. A similar thing plays out when we are doing chemical reactions. So let me go ahead and let me see, where's my other example for this? Ah, there it is. So let me go ahead and switch this up for you. So just like with the bread and cheese scenario, we can have the same thing going on between particles of reactants. So in this example, we've got hydrogen and chlorine as the reactants, and of course they form hydrochloric acid as the product, and there's some leftover hydrogen in this scenario. So when you're given different starting amounts of different substances, you have to be able to recognize that the amount of product you get is limited by whichever reactant runs out first. In the scenario that you see here, you ran out of chlorine before you could run out of hydrogen, so you have some leftover hydrogen that has no chlorine to react with. If we go back to the bread and cheese scenario, you ran out of cheese before you could use all your bread. So the same way the cheese limits the number of sandwiches that you can actually make, in this example, the chlorine limits the amount of hydrochloric acid you can make since it runs out first. So the ultimate rule here is whatever runs out first dictates, limits the maximum amount of product that you can actually get. And limiting reactant problems are really all about figuring out which item runs out first. Let's just go ahead and jump straight to some examples. Actually, before that, maybe I should talk about percent yield. Yeah, let's talk about percent yield, and then we'll jump over to some limiting reactant and percent yield problems. So let me go back to our document camera. And let's go ahead and write down our definitions. So a limiting reactant runs out first. Runs out first. An excess reactant will have some leftovers. And of course, we have some fancy abbreviations for limiting reactant and excess reactant. For limiting reactant, it's pretty intuitive. A limiting reactant would just be abbreviated LR. But for the excess reactant, here's how we abbreviate it. I know, it's stupid, but it works. It's just the letter X and then the letter S, excess. Don't you just love the English language? Anyway, the other thing that we've been neglecting so far, and that we'll probably continue to neglect for a long time, is percent yield. The percent yield of a reaction. So the percent yield of a reaction is basically the efficiency of that reaction. Real reactions almost never give you the amounts that you calculate when you do stoichiometric calculations. Real reactions will usually give you some percentage of what you expect. The formula for the percent yield of a reaction is the actual yield, so the actual amount of product that you got, divided by the theoretical yield, what you would assume you'd be getting based on calculations, times 100%. And percent yield should never be more than 100%. that would mean that you did something horribly wrong with one or more of your calculations. But yeah, percent yield is equal to the actual yield over the theoretical yield times 100%. So as an example, let me go back to one of these problems that we did. Hopefully one for which we actually did all the calculations. I skipped the calculation there. That's not a product, so that's not going to do us any good. Is this one? Okay, yeah, this one right here. So, wait, is that 10 to the 1? That's supposed to be 10 to the 2. That's supposed to be 10 to the 2. Great. That's a mistake I'm going to have to point out in a pinned comment later. Okay, so in this calculation, we said that the 2.6 liters of hydrochloric acid that we put in at a concentration of 1.44 molar would give us 210 grams of gallium chloride. So 210 grams, that's your theoretical yield. That's what we expect to get if we put in this much hydrochloric acid. What if instead I got 180 grams of gallium chloride? What if instead of 210 grams, I got 180? What if my actual yield was 180 grams of gallium chloride when I was expecting 210 grams of gallium chloride? Then my percent yield, the efficiency of the reaction, would be, let's go ahead and calculate this real quick, 18 over 21. So that's 0.86. If we keep 2 sig figs and multiplied by 100, that would be 86%. So you can say that the efficiency of that reaction, if we actually do it, and it gives us 180 grams instead of 210, you could say it's only 86% efficient. We only get 86% of what we want. And why does this happen? Well, there could be any number of reasons why this happens. One reason is that you might just have contaminants in the equipment that you use. You could have like side reactions. Maybe there's something in there that reacts with your hydrochloric acid or reacts with some of it so that it doesn't all react with your gallium whatever it was we had to form gallium chloride. Let me see, what did we have? Oh, it was just raw gallium. Okay. So yeah, there might be something that just reacts with the hydrochloric acid and uses up some of it before it can all be used on the gallium, so you end up with less gallium chloride because of that. You could just have a reaction that reaches equilibrium before it goes to completion. You could have reactions reaching equilibrium. Reactions may reach equilibrium before going to completion. Equilibrium is a big topic that we will discuss in a much later chapter. But yeah, reactions may reach equilibrium before completion. Let me wall that off. And once a reaction reaches equilibrium, if it's capable of achieving an equilibrium, it will generally stay there and not go forward anymore. We'll understand how equilibrium works and why it works the way it does, again, in a later chapter. But yeah, that's the concept of percent yield. And if you already know the percent yield of a reaction, then you can calculate the actual yield. If you know the percent yield, then you can calculate the actual amount you are going to get beforehand so that you won't be surprised when you end up with less than what you expected. So that's percent yield. There's limiting versus excess reactants. We've talked about them. Now let's try playing around with them. I've got two quick examples of percent yield, and then we'll look at more stoichiometry problems that actually include considerations for limiting reactants. So first up, I've got, let's move on to this screen. I've got a sample of 0.53 grams of carbon dioxide was obtained by heating 1.31 grams of calcium carbonate. What is the percent yield for this reaction? That's all it says, and that's all it needs to say. So let's go ahead and switch back to our camera. So we've got 0.53 grams of carbon dioxide. That's the actual yield. And by the way, the actual and theoretical yield, they can be in grams, they can also be in moles. So either actual moles over theoretical moles or actual grams over theoretical grams, and I guess you could also do actual liters over theoretical liters in some cases. But yeah, 0.53 grams, that's our actual yield. So that's our actual yield of carbon dioxide. Let me see. And then what they did was they heated 1.31 grams of calcium carbonate. So they took calcium carbonate and heated it up, decomposing it into calcium oxide and carbon dioxide, and that equation is completely balanced. So 1.31 grams of calcium carbonate is what we started with. Based on the calcium carbonate that went in, how much carbon dioxide do you expect? Should be a rather simple calculation. 1.31 grams of calcium carbonate. Converting that to moles, we've got every, let's see, 1 mole of calcium carbonate gives us roughly 100 grams, if I remember it from the last video. Calcium is 40.078. And carbonate, we've got 12.011 for carbon, 3 times 15.999 for oxygen is 100.086. 100.086 grams of calcium carbonate. Okay, and then converting moles, I could honestly just skip this because it's just a 1-to-1 ratio. 1 mole of calcium carbonate gives us 1 mole of carbon dioxide, and then molar mass of carbon dioxide is going to be 12.011 plus 2 times 15.999 is 44.009. I probably should have remembered that from earlier. Every 1 mole of CO2 gives us 44.009 grams of CO2. All right, let's work out the numbers. So 1.31 over 100.086 rounded to 3 sig figs is 0.0131 moles, and it'll still be 0.0131 here because it's just 1 over 1. And then multiplied by 44.009, 0.0131 times 44.009, rounding to 3 sig figs, that's 0.577. So I'm getting 0.577 grams of CO2. So that's my theoretical yield. This is my theoretical yield. I guess, yeah, I'll try to squeeze in the word yield here. Theoretical yield. There, it fits. And yeah, we can calculate percent yield. So percent yield of carbon dioxide is going to be actual yield 0.53 over theoretical yield 0.577 times 100%. You could include the grams if you want, but they cancel out, so I don't see much point in doing it, other than, I guess, just developing the habit to make sure you don't accidentally divide grams by moles or something, making sure that the units do actually match up. So I guess that would be the point of doing it, just as a safety precaution. But yeah, 0.53 over 0.577 times 100%, that's going to round to 2 sig figs, so 92%. 92%. Okay. So that's one type of percent yield problem you can do. The other type is also pretty simple. The other type gives you the percent yield up front and asks you to calculate actual yield. So we've got citric acid, which is a component of jams, jellies, and fruity soft drinks, is prepared industrially via fermentation of sucrose by the mold Aspergillus niger. The equation representing this reaction is sucrose plus water plus 3 oxygen gives you 2 citric acid plus 4 water. What mass of citric acid is produced from exactly 1 metric ton of sucrose if the yield is 92.30%? Okay, so we need the molar mass of sucrose, which I think is around 343. You're probably better off Googling it rather than calculating it, but I've shut off my Wi-Fi so that I don't get distracted by any notifications while recording, so I can't really do that right now. Well, I guess I could use my phone. Yeah, let's do that. I'm going to use my phone and just Google it. Molar mass of sucrose. Okay, to the Google. Any day now. Molar mass sucrose. And according to Google, I'm getting 342.3 moles, so I was almost right. And you cannot see my my camera right now. Oh well. That's fine. Let me go ahead and switch back to our camera. So I'll try to fit this all on one page, save a twig. But yeah, so sucrose, maybe I should copy the reaction first. So C12H22O11, we've got, it's 342.3 grams per mole. And that's going to react with water and oxygen. And then, interestingly enough, it reproduces water along with your citric acid. So 2C6H8O7. I'm going to want to Google the molar mass for that too. Plus 4 waters. So if I were the one writing this reaction, I would just subtract a water from both sides and say it overall produces 3 water. But I guess you need to have some water in the beginning to get the reaction started. So that's probably why they included it there. Let me look up the molar mass of citric acid real quick. Citric acid is 192.124. Citric acid says 192.124. This might disagree with the calculation for the molar mass that you get from your periodic table, since not all periodic tables use the same level of precision, and periodic tables do get updated periodically, no pun intended. So, depending on whether or not you're using the most up-to-date periodic table, you may or may not agree or disagree with Google's molar masses here. But yeah, I'll shut this off for the time being and keep it handy in case I need it later. Okay, we've got the molar masses of those two. What mass of citric acid is produced from exactly 1 metric ton? So 1.000 times 10 to the 3 kilograms of sucrose if the yield is 92.3%. Okay, so we've got 1 metric ton of sucrose, so 1.000 times 10 to the 3 kilograms of sucrose. I'm not going to write that all out. Convert it from kilograms to grams, so 1 kilogram equals 1,000 grams. And that just makes it 1.000 times 10 to the 6. And then we convert from grams of sucrose to moles of sucrose, so 342.3 grams of sucrose gives us 1 mole of sucrose, and then every 1 mole of sucrose gives us 2 moles of citric acid, and then every 1 mole of citric acid gives us 192.124 grams of citric acid. And that's our theoretical yield. And once we have our theoretical yield, what we can do is multiply it by the percent yield to get our actual yield, right? Theoretical yield multiplied by percent yield on both sides gives us the actual yield times 100%. So I suppose we'd also have to divide by 100. But yeah, so let's go ahead and grab our calculator. So we've got 1 times 10 to the 6 essentially, times 1 over 342.3. So divide by 342.3. Whoops, didn't mean to do that in the exponent. Divide by 342.3. And that keeps us with 4 sig figs, so 2921. 2921 is what we've got so far. 2921 moles of sucrose. And then multiply that by 2. So 2921 times 2 is 5842. 2 moles of citric acid, and then multiply that 5842 by 192.124, and that gives us a really big number, but we have to round it, so it's 1,122,000, or 1.122 times 10 to the 6. 1.122 times 10 to the 6 grams of citric acid. That's the theoretical yield, and of course if we take our theoretical yield, can I still fit it on this paper? Let's try and do it here. If I take our percent yield, which was 92.30 according to the problem, equals actual, I'll just call it A, over theoretical, which is 1.122 times 10 to the 6, times 100%. Divide both sides by 100, that just changes this to 0.9230, and multiply the theoretical yield on both sides, multiply it over to there, and that'll give you your actual yield. So 0.9230 times 1.122 times 10 to the 6 gives us, if I round it to, let's see, 4 sig figs still, then that'll be 1.036 times 10 to the 6. 1.036 times 10 to the 6 grams of citric acid, also known as 1036 kilograms, or sorry, 1036 times 10 to the 3 kilograms of citric acid, or 1036 metric, wait, no, is it 1036 metric tons? No, it's 1.036 metric tons. 1.036 metric tons. Okay, so we get 1.036 actual metric tons of citric acid from 1 metric ton of sucrose, which kind of makes sense. It does seem like the amount of citric acid you would get should weigh somewhere close to the same amount as the sucrose, because the number of carbons in 2 citric acids is the same as carbons in the sucrose. The number of hydrogens is almost the same, and the number of oxygens is a little more when you take 2 citric acid molecules into account. So yeah, they should kind of have similar masses coming out. Okay, and that's your second percent yield example. Now let's take a look at a couple problems with limiting reactants, and then I'll give you the golden question for homework, and then we'll talk about solutions and solubility. Oh yeah, we're nowhere near done yet. We are nowhere near done yet. Well, we're probably past the halfway point in my estimation, but my estimations are usually not that trustworthy. So let's see. Up here, we'll just do a couple of these real quick and try not to take too long. So number 70 says outline the steps needed to determine the limiting reactant when 30 grams of propane is burned with 75 grams of oxygen, and determine the limiting reactant. Let's go ahead and do that. So propane, C3H8, you'll learn how to name that when we cover organic chemistry. Propane combusts with oxygen to give us, assuming it's complete combustion, since they didn't specify. Always assume combustion is complete unless they say otherwise. We get carbon dioxide and water, and first thing we need to do is balance. So let's see. We've got balance the carbons and hydrogens first, so I'm going to start with a 3 here and a 4 here. That would give me, well, that would even my numbers of oxygen on this side, and I can only get evens on this side, so that should actually work. 3 carbon dioxides, 4 waters, 3 carbons here, 3 carbons there, 4 times 2, that's 8 hydrogens here, 8 hydrogens there. 4 oxygens from the water, and 3 times 2, 6 oxygens from the carbon dioxide. That's 10 on the right hand side, so 5 times 2 gives us 10 oxygens on the left. All right, it's balanced. Now then, they gave us 30 grams of propane and 75 grams of oxygen. So our first task is to figure out which of these we should rely on. Which of these should we rely on to determine how much actual product we get? Well, in this case, actually, the only thing they asked was determine the limiting reactant. They didn't ask us to calculate any product at all, but that's okay. So there's two different ways, two common techniques for determining the limiting reactant. One is to just pick either one of the reactants and calculate how much of the other reactant would be needed to react with it completely. And that's the way I prefer to do it. The other way of doing it is pick one of the products, it doesn't matter which one, pick a product and calculate how much product you could make with each reactant, and whichever reactant produces less product is the one that's going to run out first. It's kind of like if we go back to the bread and cheese example. If we calculate how many sandwiches you can make with the bread, we had 28 slices of bread, which would make 14 sandwiches. And we calculate how many sandwiches you could make with the cheese, you had 11 slices of cheese that could make 11 sandwiches. Well, can you make 11 sandwiches or 14 sandwiches? You can only make 11 based on the cheese. So you could just calculate the product based off of each of the reactants and go with the one that produces less, because that's the one that's clearly going to run out first. Okay, so that's the second method, and the second method, I guess, requires less mental work and more paperwork, and that's why I prefer the first method, but I imagine a lot of beginner students would prefer the second method since it doesn't require as much guesswork. I'm just going to cover both. So I'm going to cover the first method first. So I'm going to pick either one of these. I'm going to pick the propane, and I'm going to start with propane and calculate how many grams of oxygen it would need to react with in order to use it all up. So 30 grams of propane let me just Google the molar mass of propane to save time. Molar mass, and I'm going to type in propane, is 44.1 grams per mole. 44.1 grams per mole. Oxygen gas, its molar mass is approximately 32. So I'm going to round it to 4 sig figs, 32.00 grams per mole, because I'm kind of sick of 15.999. I'm just rounding it to 16.00. So there you go, 32 grams per mole. And let's see. So 44.1 grams of C3H8 gives us 1 mole of C3H8. Then we can calculate the moles and grams of oxygen. So every 1 mole of C3H8 gives us 5, or requires 5 moles of oxygen to completely react with. And every 1 mole of oxygen gas gives us, or is about 32 grams of oxygen gas. Let's go ahead and calculate what we've got here. And since this is just a quick test to determine whether or not it runs out, I can probably get away with not being too specific about my sig figs, but I'm going to be careful with my sig figs anyway. So 30.0 over 44.1 is 0.680. 0.680 times 5 over 1 is 34.0. 34.0 times 32.00 over 1 is, I guess I would round that to 11, or no, 109. So 109 grams, keeping it at 3 sig figs. So 30 grams of propane is enough to react with 109 grams of oxygen. Do I have 109 grams of oxygen? No, I have 75 grams of oxygen. I have enough propane to react with more oxygen than what I have, so the oxygen runs out first. I know a lot of people are extremely confused by that sentence, which is why I'm going to cover the second method that requires less guesswork, but I do think it's worth it to take the time to really think about this method and how it worked. Alternatively, if I had started with the oxygen, I would have calculated that the amount of propane required to react with 75 grams of oxygen is something less than 30 grams, and that would help me realize that I have more than enough propane, therefore propane is the excess reactant. But either way, we can go ahead and label oxygen as the limiting reactant and propane as the excess reactant, and for those of you who still don't believe me, we can use the second method. So second method is start with both of your reactants and pick one product. It doesn't matter which one you pick, as long as you pick the same one for both calculations. So let's see, 75.0 grams of oxygen. And let's go ahead and start setting up our calculations here. Let's calculate the moles of carbon dioxide produced. I don't have to go all the way to grams. Let's go ahead and compare the moles of carbon dioxide that each of these can produce. So let's see, grams of C3H8, 44.1 grams per mole, so there we go with that. And then for every, it looks like 1 mole of C3H8, we get 3 moles of CO2. And I can just stop there. I don't have to go any further, at least not for this problem. If it was a problem asking for final grams of product, then I'd have to add a step for at least one of these. 75 grams of oxygen, we know every 32.00 grams of oxygen is 1 mole of oxygen, and we know from our balanced equation that 5 moles of oxygen go into getting 3 moles of carbon dioxide, 3 moles of CO2. And we can go ahead and perform our calculations here. So calculator, 30.0 divided by 44.1 is 0.680. 0.680 times 3 is 2.04. So this one's giving me 2.04 moles of carbon dioxide. Meanwhile, this one is going to give us 75.0 divided by 32 is 2.34. 2.34 times 3 over 5 is 1.40. 1.40 moles of carbon dioxide. So I have enough propane to make over 2 moles of carbon dioxide, but I only have enough oxygen to make 1.4, so I'm never going to reach 2.04 moles of carbon dioxide with what I have. So oxygen produces less product, therefore oxygen is the limiting reactant. It requires more writing. As you can see, you have to do all of this versus just this. And maybe to you it's worth it. It depends on whether you care more about saving paper or just avoiding driving yourself insane with trying to make sense of the result of method 1, but my preference is method 1, and method 1 is probably what I will stick with most of the time. And you did not see any of that. Oh goodness, I forgot to change the screen. Well, you can see my results now. I guess I'm gonna have to edit that part in. Oh goodness. Yeah, I suppose what you can do then to recover from this situation is just open this in a separate tab and listen to the audio from the last few minutes again. But yeah, let's go over that real quick again since you missed it all. I can't believe I forgot to do that. Listed all of the molar masses here, labeled my starting amounts of propane and oxygen. Of course, once I found out that I get 109 grams of oxygen required to react with my 30 grams of propane, I decided to label the propane as the excess reactant and oxygen as the limiting reactant, and this is where I started doing the calculations for method 2. So here's method 1, and here's method 2. Method 2 takes up a little bit more space on the page, but again, like I said, it might still be worth it to you in that it reduces confusion. But honestly, I think it is worth it to make sense of how this first method works. I think it'll make you into a better chemist if you can make sense of it. And now I've got a fly bugging me, of course. Let's go ahead and look at another limiting reactant problem. And maybe this time you'll actually get to see me working it. So, number 71 says, outline the steps needed to determine the limiting reactant when 0.5 moles of chromium and 0.75 moles of phosphoric acid react according to the following chemical equation. And we've seen that chemical equation before. 72 says, what's the limiting reactant when 1.50 grams of lithium and 1.50 grams of nitrogen combine to form lithium nitride, a component of advanced batteries, according to the following unbalanced equation? I think I would rather go with 71. So I'm just going to do the setup for determining the limiting reactant. And this time I'm not going to forget to switch back to my camera. So 71, outline the steps needed. So we've got 0.50 moles of chromium. Oh, they made this easy for us. So we've got chromium, 2 chromium specifically, plus 2 phosphoric acid, gives us 2 chromium phosphate, chromium 3 phosphate to be specific, plus 3 hydrogen gas. Let me see, and they started us off with 0.50 moles of chromium and 0.750 moles of phosphoric acid. In this case, the limiting reactant is a little extra obvious because the balancing coefficients of both reactants are the same. When the balancing coefficients of both reactants are the same, then whichever one has less moles is the limiting reactant. But if you don't believe me, we can go ahead and calculate it. I'm going to do it using method 1, so let's pick the chromium. I've got 0.50 moles of chromium. How many moles of phosphoric acid can it react with? So for every 2 moles of chromium, I can react with 2 moles of phosphoric acid. 2 over 2 is just 1, so the 0.50 moles of chromium would react with 0.50 moles of phosphoric acid. Do I have 0.50 moles of phosphoric acid? Yes. In fact, I have more than 0.50 moles of phosphoric acid. So the chromium is going to run out. Chromium is the limiting reactant this time. And the phosphoric acid, I will have some left over. Specifically, I'm going to have 0.25 moles of phosphoric acid left over. Alright, and that takes care of another simple limiting reactant problem. Now let's take a look at some trickier ones. So it says uranium can be isolated from its ores by dissolving it as, I guess I would call that uranium dioxide dinitrate. Then separating it as solid uranium dioxide oxalate trihydrate. That's my best guess as to the name. Addition of 0.4031 grams of sodium oxalate to a solution containing 1.481 grams of uranyl nitrate, or uranyl nitrate rather, yields 1.073 grams of solid whatever that thing is. Uranium dioxide oxalate trihydrate is my best guess for its name. The reaction is given. Determine the limiting reactant and the percent yield of the reaction. If determining the limiting reactant is... Oh, well, I guess if they want us to get the percent yield, then... Is it worth doing? Okay, I'll at least set it up. I don't know if we're going to do the percent yield part of it, though. So they gave us a reaction. Sodium oxalate reacts to what I'm unofficially calling uranium dioxide dinitrate. And 3 waters. To form uranium dioxide. I don't know why they included the oxalate in parentheses, but oxalate trihydrate. And I guess uranium would count as a transition metal, so I would probably call this uranium-6. But now I'm obsessing too much over what to call it. Anyway, that plus 2 sodium nitrate, it looks like. Plus 2 NaNO3. And I didn't have enough space for it, I'll just write it down here. Plus 2 NaNO3. Yeah, I didn't gain much by shifting this down a line. Poor planning. Oh well. Let's carry on with, I'll use peach. So determine the limiting reactant and the percent yield of this reaction. They've given us 0.4031 grams of sodium oxalate, 0.4031 grams of sodium oxalate, and they've given us Let's see, so 1.481 grams of, I guess they're calling it uranyl nitrate. 1.481 grams of uranyl nitrate, and then the yield of the solid is 1.073 grams. So we end up with 1.073 grams of actual yield for this product. Okay, let me see. So I guess we're going to need the molar masses of everything in here, so I'm going to just try and Google them. I think it'll be faster to Google them rather than calculate them. So molar mass of sodium oxalate is 134 grams per mole. Somehow I get the feeling I should have more precision than that, but I'll settle for 3 sig figs. 134 grams per mole. And then molar mass of uranyl nitrate. Is 394.04. 394.04 grams per mole. And then this one I'm probably just going to have to type out. Unless I'm going to take a guess at its name. I'm going to call it uranyl oxalate trihydrate. I'm just going to take that as a guess at its name and hope I'm right. And I'm not seeing anything, so go back to that, and that doesn't seem to work out too well either. Okay, I guess I'm just going to have to calculate this one from scratch. Oh well, it was worth the effort. So uranium 238.029 plus 2 oxygen, 2 times 15.999 plus, well actually there's more oxygen in there, plus 2 times 12.011 plus the 4 oxygens in the oxalate plus 3 waters. So water is about 18.02, and I'm going to round that to 2 decimal places, so that's 412.11. 412.11 grams per mole. Okay, there we go. That should be everything we need to solve this problem. Now then, question was determine the limiting reactant and the percent yield of the reaction. So determining the limiting reactant, I'm just going to use method 1. So I've got 0.4031 grams versus 1.481 grams. Balancing coefficients are 1s. I need to figure out the numbers of moles, right? I can't just, even though the balancing coefficients are the same, I can't compare them directly until I get them in moles. So 0.4031 grams divided by 134 grams for every mole, that gives me 0.00301. So 0.00301. and that's the moles, versus the uranyl, so that's going to be 1.481 grams divided by 394.04 grams per mole is 0.00376 moles of uranyl. So every 0.00301 moles of sodium oxalate, if I have 0.00301 moles of sodium oxalate and every 1 mole of sodium oxalate reacts with 1 mole of uranyl, then that would mean I can react with 0.00301 moles of uranyl, which I do have. In fact, I have more than that. So uranyl is the excess reactant here, and sodium oxalate is the limiting reactant. And now that I know my limiting reactant, all calculations must be based on the limiting reactant from here on out. So I could calculate how much leftover uranyl I have from the limiting reactant. I would say that according to this limiting reactant, I use 0.00301 moles of uranyl because there's a 1-to-1 mole ratio between them. And that would leave me with 0.00075 moles of uranyl left over, and you could multiply that by 394.04 to get the leftover grams of uranyl. That's not the problem that we have, but it is something you can do. It's something you can calculate. Which color should I use? I guess I'll go for navy blue. At least I think it's navy blue. We want to figure out the theoretical yield of this solid, this hydrate of ours. So let's go ahead and start with 0.00301 moles of our limiting reactant. And let's see, for every 1 mole of sodium oxalate, we get 1 mole of the solid. So that's just a 1 mole ratio, a 1-to-1 mole ratio, which changes nothing. And then that means we've got our moles of this compound now. We can multiply every 1 mole of this uranium compound has a mass of 412.11 grams. So now we can calculate the theoretical yield. 0.00301 times 412.11 gives us 1.24 if we round it to 3 sig figs. 1.24 grams is what we would expect as a theoretical yield. Our actual yield is 1.073, so we can do 1.073 actual yield over 1.24 theoretical yield times 100%, and our percent yield is, drum roll please, 1.073 over 1.24 times 100% is 86.5%. 86.5% yield of this uranium hydrate compound. Alright, and there's that. I think the next two are much easier in comparison. So 74 says how many molecules of C2H4Cl2, I guess that would be dichloroethane, can be prepared from 15 ethylene molecules and 8 chlorine molecules. Okay, so for this one you can just count the numbers of atoms, and I guess we need to write a balanced equation first, so let's go ahead and do that. So we need to make dichloroethene or dichloroethylene, or sorry, ethane, dichloroethane, from ethene, which is going to be C2H4, and chlorine. And that's going to give us C2H4Cl2, all 1:1:1 ratios here. All the balancing coefficients are 1s. They gave us as starting amounts 15 molecules of C2H4, and 8 molecules of Cl2. Okay, this one should be simple, straightforward. Now that I'm looking at it, the answer is staring me in the face. You can only make 8 of these, because you need 1 molecule of chlorine for every molecule of dichloroethane, and you need 1 molecule of ethylene for every 1 molecule of dichloroethane. So yeah, once you use up your 8 molecules of chlorine, you've made 8 molecules of dichloroethane, and you'll have 7 leftover ethylene molecules. Okay, that one was pretty easy. So answer is we can make 8 molecules. Okay, let's take a look at number 75. They have a nice drawing there for us. How many molecules of the sweetener saccharin can be prepared from 30 carbon atoms, 25 hydrogen atoms, 12 oxygen atoms, 8 sulfur atoms, and 14 nitrogen atoms? So I'm going to write down the chemical formula for this. First, let's count the carbons. I see 1, 2, 3, 4, 5, 6, 7 carbons in that structure, so C7. I see how many hydrogens? I see 1, 2, 3, 4, 5 hydrogens, so C7H5. Nitrogen, I see just 1, so that's an N. Oxygen, I see 3. And I see 1 sulfur. And I think that's everything that's in there. Okay, and they told us we've got 30 carbon atoms. They told us we've got 30 carbon and 25 hydrogen and 12 oxygen. I guess I'll write that with a curly O. And 8 sulfur and 14 nitrogen. Let's switch back to the camera. I wonder how many people were freaking out that I hadn't switched earlier. Okay, so I guess if you want to make a sort of pseudo reaction to produce this compound, you could write it as yeah, I guess we can just make this sort of pseudo reaction. We can say 7 carbon plus 5 hydrogen plus nitrogen plus 3 oxygen plus sulfur gives you C7H5NO3S. And yeah, as for the order in which to list these, a good rule of thumb is Schnops, CHNOPS. Where P is phosphorus, that's not included in this particular compound, but yeah, list them in Schnops order when you've got something that goes beyond just being a mere hydrocarbon and actually starts including more elements. C first, then H, then N, then O, then P, then S. And of course, don't include them if they're not actually present. But now I'm rambling. So we need to figure out what the limiting reactant is here. Oh boy, we're going to have to compare all of these. So let's see. I've got 25 hydrogen. Let me start with that. So my 25 hydrogen can make 5 saccharin. Yeah, I think I'm going to use method 2 for this one. 5 saccharin. And I guess I'll just abbreviate it SAC from now on. So 25 hydrogens can make 5 saccharin. 30 carbons can make, well, once I use up 28 carbons, that's as much as I can do because you have to use 7 at a time. So it looks like you can make 4 saccharin out of the 30 carbons that you have. From the oxygen, I've got 3 oxygen needed. So with the 12 I have, I can make up to 4 saccharin. With the 8 sulfur, you only need 1 sulfur for each saccharin molecule, so you can make 8 saccharin molecules with 8 sulfur atoms. And with 14 nitrogen atoms, it looks like you can make 14 saccharin molecules, so it looks like we can make 4 molecules of saccharin. We will have some leftover carbon, 2 leftover carbon atoms, 5 leftover hydrogen atoms, no leftover oxygen. We'll have 4 leftover sulfur, and we'll have 10 leftover nitrogen. And there you go. So for homework, and I mean, I guess it's up to you whether or not you actually do it, but here's a fun little question. It's not going to be too hard, but now you know how to do it. You have the gold question. So the question is, would you agree to buy 1 trillion gold atoms for $5? Explain why or why not, and you can find the current price of gold at CNN Money, and they gave you a conversion factor. 1 troy ounce is equal to 31.1 grams. So I already did look up the cost of gold, the current price of gold. So let me go ahead and put that in front of you. There it is right there. If you go to that website and you go to the metals section, then you'll see the price of gold along with the prices of silver and platinum and copper. And on the day that I looked this up, the price of gold was sitting at $1,452.50 per troy ounce. So you can base it off that number, or you can go to the website yourself and figure out what the cost of it is today if you don't want to use the data from the day that I pulled this. And yeah, maybe I should start investing in gold, because over the past 52 weeks there was a point where it was at 1,167, and today, or at least the day I picked this up, it was 1,452. What an investment. It's probably not the smartest investment. I don't know. I listen to different financial advisors slash analysts slash personal finance people, and they all have different opinions on whether or not you really should invest in gold. So don't take your financial advice from me. Go try someone like, on YouTube there's, I think, a series called Money School by Preet Banerjee. You might want to look up that person. But now I'm rambling too much and making this video even longer. So let's go back to my camera, and now let's move on to a new topic. we're done with introducing stoichiometry and getting rid of our rose-colored glasses and acknowledging the reality of limiting reactants and percent yield. Now it's time to move on and talk a little bit more about some things you can do with solutions. So, specifically, I want to talk about reactions like the very first one I started with for this video. Let me go ahead and dig that one back up. This is going to take a while. Ah, there we go. I might as well just bring this up to the front. Okay, so this reaction I have right here. I've got a reaction between sodium phosphate and calcium bromide, producing sodium bromide and calcium phosphate. So this, as you may remember from from part 1 of the series, from the first video, you might remember that this is an example of what's called a double displacement or double replacement reaction. So this is an example of a double replacement reaction, but it also has another name. This is a specific kind of double replacement reaction, which is also called a precipitation reaction. You can also call this a precipitation reaction. You can also call it a precipitation reaction. So precipitation reactions are specific types of double replacement reactions. Precipitation reactions are a type of double displacement reaction, or double replacement reaction. In which a precipitate is formed. What on earth is a precipitate, you might ask? Some of you already know, but for those who don't know, a precipitate is basically a solid that gets formed when you mix 2 or more solutions. At least that's my running definition for the time being. If I need to refine the definition later, then I will, but for now, a precipitate is just a solid that can be formed when you react 2 or more solutions with each other. So precipitation reactions are a type of double displacement reaction, and by the way, I didn't mention this the last time I talked about double displacement, but double displacement can also be called metathesis. Double displacement or double replacement reactions can also be called metathesis reactions. And metathesis actually comes from linguistics. In fact, I dug this interesting tidbit up on Wikipedia. Let me show it to you. Where did I put it? Wait, did I not include it in here? I don't think I included it. I could have sworn I had it ready. That's so weird. I could have sworn I had it ready. Oh well, if you go to the Wikipedia page for the word metathesis, it shows you a bunch of examples of what metathesis means in the English language. And there are different kinds of metathesis in English, but the main type of metathesis that they mention in the very beginning is when you swap the places of the sounds of 2 letters in a word. kind of like when people say asterisk instead of asterisk. So when people pronounce the word asterisk as asterisk, or when people try to ask you a question instead of ask you a question. So those are examples of metathesis. You're exchanging the places of the two sounds. And that's kind of what double displacement is, right? You're just, where did I put it? There it is. That's what double displacement is. You're just making the ions exchange partners. So the sodium and calcium trade partners with each other. Sodium pairs up with bromide and calcium pairs up with phosphate. So yeah, I thought that was just an interesting little tidbit to include. I can't believe I forgot to set it up though. I could have sworn I had it ready somewhere, but apparently not. Oh well. Where was I going? Right, so precipitation reactions. In order to be able to properly analyze precipitation reactions, you need to be able to identify what the precipitate in the reaction is. So if you just so happen to know that calcium phosphate is a solid that doesn't dissolve well in water and that it would drop out when you perform this reaction, then you'd already know that this would be our precipitate. You would already know that calcium phosphate is our precipitate, which is sometimes abbreviated PPT. Because that abbreviation isn't used for PowerPoint already, chemists decided to hijack it. Actually, they were probably using it long before PowerPoint was invented, so Microsoft lawsuit? Probably not. I'd have to figure out who used it first, but PPT is used as an abbreviation for precipitate. So calcium phosphate is the precipitate, but how do we know that? Aside from, just memorizing a bunch of compounds and their properties. How do we know that calcium phosphate is the solid that drops out when you mix these two solutions with each other? Well, that's where the solubility rules come into play. So let me go ahead and show you this slide. So they're called solubility rules, but really they're solubility guidelines, because if you know anything about chemistry, you know in chemistry there aren't really any rules. There are patterns with lots and lots of exceptions. But yeah, if you want rules, study physics. If you are okay with not having rules and just having general trends and patterns, then chemistry might be a good fit for you. Anyway, you've got that table of solubility rules. I've taken it from my Jesperson Hyslop textbook. It's also one of the textbooks I mentioned in a pinned comment for the first video of the series. And it says, for soluble compounds, all compounds of the alkali metals are soluble. So the alkali metals, if we look at our periodic table, are all the metals in that red block. So anytime you see lithium, sodium, potassium, rubidium, cesium, or francium, any compound containing those metals will be soluble in water. It will dissolve in water rather easily. Then it says all salts containing the ammonium ion, the nitrate ion, the perchlorate ion, the chlorate ion, and the acetate ion are soluble in water. Rule number 3 says all chlorides, bromides, and iodides, which are salts containing, of course, Cl-, Br-, or I-, are soluble except when combined with silver, lead 2, and mercury 1. I mentioned towards the beginning of this video that we were going to be seeing mercury 1 again. There it is. I mentioned it in part 1 of the series. Mercury 1 is not just one atom of mercury with a charge of positive 1. It's two atoms of mercury with a combined charge of positive 2. I don't know why mercury does this, but it's something you need to know. Mercury 1 is not Hg+, it's Hg2 with a 2+. So remember that. Mercury 1 is not what you would expect it to be. So yeah, basically silver chloride is not soluble in water. It would drop out as a solid if any silver ions ever came into contact with chloride ions. Same thing with lead 2 chloride, same thing with mercury 1 chloride, or bromide, or iodide. If those ions mix, their attraction to each other is so strong that the water molecules can't separate them from each other very easily, so most of it will drop out as a solid, and a very, very, very tiny amount will actually be dissolved in the water. Rule number 4, all sulfates are soluble except lead 2 sulfate, calcium sulfate, strontium sulfate, mercury 1 sulfate, and barium sulfate. And you're going to have to memorize all these rules, by the way. Commit them to memory. I would say the most important ones to remember are the ones further up on the top. The higher up they are, the more important they are to remember. But you do want to memorize all of them. Rule number 5. So 5 says all metal hydroxides and all metal oxides are insoluble except those of the group 1 metals and those of calcium, strontium, and barium. So yeah, that kind of agrees with rule number 1, because rule number 1 said all of the group 1 metals will be soluble no matter what you pair them with. So yeah, all hydroxides and oxides are insoluble except the ones that are always soluble, which are the ones with the group 1 metals and calcium, strontium, and barium. Also, they mention when metal oxides do dissolve, they react with water to form hydroxides. And there's an example of that. Sodium oxide reacts with water to form sodium hydroxide rather than just dissolving in water. And rule number 6 says all salts that contain phosphate, carbonate, sulfite, and sulfide are insoluble except those of group 1A, following rule number 1, and the ammonium ion, following rule number 2. I would add to this the oxalate and chromate ions. So I would modify rule number 6 and say all salts containing phosphate, carbonate, sulfite, sulfide, and oxalate and chromate. I would add oxalate and chromate to that list. Sometimes those will show up. And yeah, so these solubility rules aren't entirely set in stone. They're just kind of common patterns that have been observed by chemists, and you just kind of go by them, and they'll be more than enough for our purposes at least. So let's go ahead with those rules in mind, try and make sense of what happens in this first reaction I gave you in the very beginning of the video. So we've got sodium phosphate. Well, rule number 6 just said all phosphates are insoluble except with the group 1 metals and ammonium ion. And sodium is one of the group 1 metals. It's in that first column of the periodic table. It's in that red block. So this is a soluble compound. It'll vanish easily when you stir it into some water. So no precipitate here. It's not a solid. Same thing with calcium bromide. So bromides and chlorides and iodides, according to rule number 3, I think, were soluble. Yeah, it was rule 3. So all chlorides, bromides, and iodides are soluble with anything except silver, lead 2, and mercury 1. Calcium is not one of those exceptions, so this is soluble. So calcium bromide, you can put it into some water and stir it in, and it'll vanish, it'll dissolve in just fine. Then you take these two solutions, you mix them together, and when you mix them together, the ions of sodium and calcium and bromide and phosphate all come into contact with each other. And when that happens, the sodium ions can pair up with the bromide ions, but anything containing sodium is soluble because sodium is a group 1 metal. That's according to rule number 1. And also according to rule number 3, all bromides except for silver, lead 2, and mercury 1 bromide are soluble. So this is soluble according to 2 different rules. Then you get to calcium phosphate. When the calcium ions come into contact with the phosphate ions, they get really attracted to each other. Rule number 6 says that all phosphates are insoluble with the exception of the group 1 metals and ammonium. Calcium is not a group 1 metal, and calcium is definitely not ammonium. So calcium phosphate is not very soluble in water. We call it insoluble, though the truth is it is soluble, it's just a very, very tiny amount. So for all intents and purposes, practically insoluble. So this thing can't stay dissolved in the water. It comes out as a solid, which drops to the bottom of your beaker or flask or whatever you're doing your experiment in. And yeah, that's basically it. You just look at everything going in, and presumably the 2 reactants are always going to be something soluble, and the 2 products, sometimes they're both soluble as well, sometimes only one of them is soluble and the other is a precipitate. So let's go ahead and just mix and match a whole bunch of these and try to do some precipitation reactions here, or at least predict the precipitate that forms. Let's do, here's a classic, let's do silver nitrate with sodium chloride. So of course, I first write out the products, and I get silver chloride with sodium nitrate. Now would be a good time to start introducing states of matter. So you saw this earlier in the video. One of the example problems we did, or actually a couple of them, had the states of matter written on the side of the substance in a chemical equation. Now I think is finally time to actually make sense of that. So let's go ahead and figure out what states these are in. I'm assuming they're solutions, of course, or that they're in water, and if they can dissolve, they'll be in aqueous solution. So let's look at silver nitrate first. According to rule number 2, all salts containing nitrates, among other things, are soluble. So silver nitrate is no exception. All nitrates are soluble, so this is soluble. We say this is in the aqueous state of matter, so in parentheses you can write AQ. The 4 states of matter that we list, or the 4 phases that we list in chemical equations, are solid, liquid, gas, all with the obvious abbreviations SL and G, and of course if it's in solution, we wouldn't really call it liquid, we would call it aqueous, and we would only call it aqueous, of course, if the solvent was water. We defined aqueous solutions earlier in this video. So those are the 4 different labels that you could put next to your elements and compounds. I'm not going to always include this. I'm only going to include it in situations where it really matters, and this is definitely a situation where it matters. We need to know what's soluble and what's not. Okay, sodium chloride, that's table salt. You should already know that's soluble in water just from life experience. But it also follows rules number 1 and 3. So it's soluble according to rules 1 and 3. Silver chloride, if we look at rule 3 again, let me put it back up on the screen. If we look at rule 3 again, it says all chlorides are soluble, with one of the exceptions being silver. Silver chloride is not soluble. So this is going to precipitate out as a solid. AgCl will come out as a solid. And then sodium nitrate, well, sodium is an alkali metal. All the alkali metals are soluble no matter what you pair them with. Same thing for nitrate according to rule 2. All nitrates are soluble, so that's going to be in the aqueous phase. Okay, and this is your balanced molecular equation. All of the balancing coefficients are 1s here. 1 silver in, 1 silver out, 1 nitrate in, 1 nitrate out, 1 sodium in, 1 sodium out, 1 chloride in, 1 chloride out. So this is what we call our balanced molecular equation. This is what we call our balanced molecular equation. We can write 2 other equations from here. We can write something called the total ionic equation, and we can also write something called the net ionic equation. So let's go ahead and do that. Let's go ahead and write our total ionic equation. So to get the total ionic equation for a precipitation reaction, or really any reaction involving ions, it doesn't have to be a precipitation reaction necessarily. To get the total ionic equation, all you have to do is take anything that's in the aqueous state and write it as separate ions. So silver nitrate is in the aqueous state, so I would write it as 2 separate ions. I would write silver ion, so that's Ag plus in the aqueous state, plus nitrate ion in the aqueous state, plus sodium chloride is soluble, so I would split that up into its component ions as well. So sodium ion and chloride ion. I hope you remember how to predict ionic charges. We covered that in video number 1. I know I've been referencing that a lot. But you know, it's really important. That video was the first video for a reason. So those are all the reactants, you can say, and then the products. I'll just write my arrow over here, and I guess I'll do products in another color to make it more readable. So products would be silver chloride is solid, so it stays solid. It doesn't split up into its component ions. That's kind of the whole point. So silver chloride stays solid. It doesn't split up into silver ions and chloride ions, except for a very, very tiny amount that we have yet to care about. We'll care about it several chapters down the road. And then of course we've got sodium nitrate, which is still in the aqueous phase, so that will remain as separated sodium ions and nitrate ions. Okay, so so the sodium ions and nitrate ions basically are not really doing anything in the reaction. What the total ionic equation tells you is, instead of thinking of these as two separate compounds, once they're dissolved in water, you can just think of the ions just moving around as separate entities. They've been separated from each other, so you can think of them as four separate reactants instead of, these two reactants. And if you look at the sodium and nitrate, they're floating around in the beginning of this reaction, and they're still floating around in the water at the end of the reaction. So they go in and then they come out, and it looks like they don't really do anything. They're just kind of hanging around there and watching the action rather than participating in it. Well, we call people who watch the action rather than participate in it spectators, and so sodium and nitrate are what we would call our spectator ions. So the sodium ion and the nitrate ion in this example are what we would call spectator ions. I guess I'll write that over here, spectator ions. Spectator ions. So they're ions that are present but don't actually participate in the main part of the reaction. Spectator ions. In this case, we've got sodium ion and nitrate ion. So spectator ions, since they don't really participate in the main event of a precipitation reaction, they might as well not be there. This is where we come up with the notion of the net ionic equation. The net ionic equation is just the summary of the action that's happening. Basically, it's the total ionic equation minus the spectator ions. The net ionic equation is basically the total summary of the reaction. Essentially, what happened in our mixture of two solutions when we mixed silver nitrate and sodium chloride. Effectively, what happened was that some silver ions came into contact with some chloride ions, and they formed solid silver chloride, which could not be turned back into ions. So this is the net ionic equation. It's just the total ionic equation after you drop out the spectator ions. And that kind of makes sense. Whenever you hear the word net, net means like the important part, minus all of the fat that you trim out. So if I take my box of herbal tea, for example, and I don't know if you can read it really well, but right here in small print it says the net weight is 0.9 ounces or 25 grams. Okay, so does that mean that this box is 25 grams? Well, let's bring out my kitchen scale and find out. All right. So I put the box on, and it's reading 62 grams. But it says on the box that it's 25 grams. Why? Because it's the net weight. It's the mass of the tea that's actually in this box. It's not including the mass of the box itself, and hopefully it's not including the mass of like the bags containing the tea. It would just be the mass of the actual, herbs that make up my herbal tea. So the net weight or the net mass of this tea is 25 grams. That's the mass without the unnecessary stuff. I don't care how many grams of box I got. I don't care how many grams of tea bags I got. I care about how much of the actual herbal tea, how much of the stuff I actually have of the important stuff. I probably worded that last sentence poorly, but I think you get what I mean. Let's go ahead and shut this down. But yeah, anytime you hear the word net, it's the summary. It's the important part once you trim out and leave out all the other unnecessary details. If we take as another example net income, a person's net income would probably be their income after taxes, right? There's no point in saying somebody made, I don't know, $100,000 and then paid, let's say, $20,000 in taxes. Instead, you could just say their net income for the year was $80,000. I wonder if somebody making $100,000 even has to pay $20,000 in taxes. If they have that kind of money, they can probably afford a lawyer who can find them a nice loophole. But what do I know? I'm not making six figures, at least not yet. Maybe someday. Let's see. So I guess we can do a couple more examples here. Let me think. Should I? I'm trying to decide what I should use as examples. Maybe I'm just better off grabbing one of my chemistry books and using examples from there. Yeah, that's what I'll do. I'll be back in a sec. Alright, chemistry book obtained. Let's go ahead and scoop out some examples. Here we go. So let's do sodium carbonate aqueous. Oh, I probably should have left that out so you could have some time to try and figure out if it is actually dissolved. But sodium carbonate with silver nitrate. Okay, so of course we can predict the products. Sodium nitrate and silver carbonate. So silver always has a charge of +1, so Ag2CO3. There we go. Okay, predict the products, assess solubilities. So sodium carbonate, I already spoiled it. It's aqueous. Silver nitrate, well, we know from our solubility guidelines that all nitrates are soluble. Putting that up there for a couple seconds. We already know that sodium nitrate is soluble from the previous example, and the last thing left is silver carbonate. If you look at Rule 6, all carbonates are insoluble, with the exceptions being the alkali metals. Silver is not an alkali metal. So silver nitrate, we said, was soluble, so it'll exist in the aqueous form. This will be in the aqueous form. All alkali metal compounds are soluble. And then silver carbonate, that's not going to be soluble. That's going to precipitate out as a solid. So silver carbonate is your precipitate. Let's go ahead and balance this equation, because this one is not balanced, unlike the previous one. So if I go ahead and look, it seems that I would need a 2 here and a 2 here. And that's it. Yeah, 2 sodium, 2 sodium, 2 silver, 2 silver, 2 nitrate, 2 nitrate, 1 carbonate, 1 carbonate. Perfect. It takes some practice, but you can definitely develop your balancing intuition and balance equations as quickly as I just did right there. It's something to aspire to rather than something to be intimidated by. Next up, we've got sodium nitrate and nickel 2 sulfate. Oh, actually, wait, before I do that next example, let's actually write the total ionic and net ionic equations. Let's write the total ionic and net ionic equations for this. So total ionic, sodium carbonate is soluble, so we've got 2 sodium ions. That's something we didn't see in the previous example. And 1 carbonate ion with a negative 2 charge gives us 2 times silver nitrate, so that's 2 silver ions and 2 nitrate ions. And I guess I'd have to label each of these as aqueous. This is definitely the most annoying part of writing a total ionic equation right here. Anyway, that gives us 2 sodium nitrate, which is soluble, so 2 sodium ions and 2 nitrate ions, both in the aqueous phase or aqueous state. And then solid silver carbonate, Ag2CO3 solid. So there's your total ionic equation. Do we have any spectator ions? Yes, we do. And they're the same spectator ions we had in the previous example. They're the sodium and nitrate ions. 2 sodium in, 2 sodium out, 2 nitrate in, 2 nitrate out. They didn't do anything. So if we remove the spectators, then our net ionic equation is, and I guess I can stuff it in here just to save some space. Our net ionic equation is 2 silver ions reacted with 1 carbonate ion to form solid silver carbonate, to form 1 formula unit of solid silver carbonate. Okay, so there's one example. Let's take a look at another one. So we've got sodium nitrate and nickel sulfate is up next. So we've got sodium nitrate. We've seen way too much sodium nitrate at this point. And nickel 2 sulfate. So nickel with a charge of positive 2, sulfate with a charge of negative 2. And of course, if we just have them swap partners, then sodium sulfate, sodium's a positive 1, so I need 2 of them to balance with the negative 2 charge of the sulfate. And then, of course, we've got nickel 2 nitrate. So that's going to be NiNO3 2. Okay, let's take a look at all of these. We're about to see something fascinating here. So, of course, sodium nitrate is soluble because anything with an alkali metal like sodium is soluble. Nickel 2 sulfate, well, if we look back on our solubility rules, Rule 4 says all sulfates are soluble with the exception of lead 2, calcium, strontium, mercury 1, and barium. Nickel is not one of those exceptions, so nickel 2 sulfate is soluble. So this is in the aqueous phase. Sodium sulfate, so of course that'll be soluble because of Rule 1. Sodium is an alkali metal. Nickel 2 nitrate, all nitrates are soluble according to Rule 2. Oh, we don't have a precipitate. Let's write our total ionic equation. It's about to get even more interesting. Oh, wait, did I balance this? No, I did not. So it looks like I just need a 2 here, and we're done. Yep, it all checks out. Okay, so total ionic equation. We've got anything that's aqueous needs to be split up into ions, and all of them are aqueous, so 2 sodium ions, aqueous, plus 2 nitrate ions, aqueous, plus the nickel 2 ion, aqueous, plus the sulfate ion, aqueous, those who have not memorized their polyatomic ions are probably regretting it right about now. So that gives us, let's see, sodium sulfate, so that's 2 sodium ions, aqueous, 1 sulfate ion, aqueous, the nickel 2 ion, aqueous, so nickel 2, aqueous, and 2 nitrate ions in the aqueous phase. Yeah, you can barely even read that. In fact, you can't read that because I can't read it. And given the resolution that my document camera will tolerate without blurring my hand too much, you definitely can't read it. I'm gonna need to get a new computer with a better processor. But that'll have to wait. I think the quality is decent enough. I think it's at least readable for the time being. Anyway, let's identify our spectator ions. 2 sodium in, 2 sodium out. 2 nitrate in, 2 nitrate out. 1 nickel in, 1 nickel out. 1 sulfate in, 1 sulfate out. All of these ions went in and came out unchanged. What's your total ionic equation? Your total ionic equation is nothing. No reaction is what we say in a situation like this. Your net ionic equation is nothing. No reaction happened here. All you did was mix 2 solutions. That's it. All you did was mix them. You didn't have a reaction. It's just like if you take a bowl and put salt and pepper and mix them into the bowl. They don't react with each other. The salt stays as salt and the pepper stays as pepper. And if you took your time, you could probably by hand pick out and separate the grains of salt from the grains of pepper over the course of maybe an hour. But or I guess the easier way to go about it would be to dissolve the salt in water and then drain out the water, because the water would dissolve the salt and not the pepper. So that would be the easier way to separate them. But now I'm going off topic. Yeah, all you did here was mix 2 solutions. Nothing else interesting happened. All you did was mix a pair of solutions. No chemical change occurred. No reaction happened. And you could get to a level where you master your solubility guidelines so well that you recognize, as soon as you look at these 2 compounds, you recognize that no reaction is going to occur. It's definitely possible. Let's do 1 more of these. And then what else do I have lined up? And then we'll talk about, I guess, some qualitative analysis and then gravimetric analysis, and then we will finally call it a video. Let's see, what's our third example going to be? So I've got sodium sulfide and copper acetate. Sodium sulfide and copper acetate. So sodium sulfide and copper acetate. I'm kind of sick of seeing sodium. They could have been more creative and replaced it with potassium or something. Sodium sulfide and copper 2 acetate, to be specific. Copper 2 acetate. Okay, so if we go ahead and just do the usual metathesis, just have them swap partners, then we get sodium acetate and copper 2 sulfide. Okay, and if I try to balance this, I would need a 2 right here. Should have left enough space for it. That balances my 2 sodiums and my 2 acetates, and I'm done. Okay, that was easy. Identify the states, so sodium sulfide, anything with sodium in it, is soluble. Sodium is a group 1 metal. Group 1 metals are soluble no matter what you pair them with. Any ionic compound that contains them is soluble. Acetates are always soluble. So copper 2 acetate will be soluble because all acetates are soluble. Speaking of all acetates being soluble, sodium acetate is soluble. If not for the acetate, then because of the sodium. And then copper sulfide. What did our solubility rules say about sulfides? All sulfides are insoluble. That's in rule number 6. All salts containing phosphate, carbonate, sulfite, or sulfide are insoluble with the exceptions of group 1 metals and ammonium. Copper is not a group 1 metal, and copper is certainly not ammonium, so copper sulfide is insoluble. This is going to be a solid. Here's a challenge for you. See if you can figure out, just by looking at this, what the net ionic equation is going to be. I encourage you to pause the video. See if you can, just by looking at this, determine what the net ionic equation will be. That's a skill you may want to develop, especially if you're preparing for the AP exam, where all of your answers in the free response when it comes to chemical equations have to be written as net ionic equations, and if you can determine them quickly and easily, you'll save some time that's better spent on tougher questions. Anyway, let's go ahead and write our total ionic equation. So 2 sodium ion plus some sulfide ion plus the copper 2 ion. This copper has a charge of positive 2, plus 2 acetate ions gives us, let's see, 2 sodium acetate, so that's 2 sodium ions plus 2 acetate ions plus copper 2 sulfide, which is your precipitate formed. Now that I'm thinking about it, I really should have included an illustration of a precipitate forming, but I guess since I have my book in front of me, I can just show it to you. Let me dig it up real quick, because I know I've got something in here that I can show you for precipitation. Ah, here we go. Yeah, so this is what it looks like when a precipitate forms. So, you know, you start out with 2 liquids that are clear. Sometimes they'll be clear but with a color to them. But the important thing is clarity. They don't necessarily have to be colorless, they just have to be clear. That's how you know that whatever's dissolved in them is dissolved well. And then once you mix the ions, you get a precipitate that will definitely have some sort of visible color to it. Sometimes it's white, sometimes it's yellow, sometimes it's black. It really depends on what your precipitate is, what color you get. But this is basically what you would see happening if you did precipitation reactions in the lab. You'd mix two clear solutions and get a cloudy solution, and after a while the cloud will just kind of settle and it'll all sink to the bottom, and that's where you're going to get your solid. You can then carefully pour out the liquid such that the solid doesn't spill out with it. That process is called decanting, by the way. Decanting is carefully pouring out the liquid part of a mixture in such a way that you don't accidentally pour out the solid with it. So that's called decanting, in case you encounter that word in your chemistry class. But back to the problem at hand. We've got 2 sodium ions are spectators, and our 2 acetate ions are also spectators. They come in and come out unchanged. So we can drop them, and our net ionic equation will be copper 2 ion in the aqueous phase reacts with the sulfide ion in the aqueous phase to produce solid copper 2 sulfide. And you'd see your mixture get cloudy, and eventually it would settle to the bottom, and you could decant your solution to isolate the solid copper sulfide. Of course, decanting will only get you so far. You're still going to need to use filtration to completely dry up the copper sulfide and, completely separate it and make sure there is no lingering sodium or acetate ions left on it. But yeah, so that's going to be our last example of that. Let me take a look. I know I have a problem in here for qualitative analysis. At least I think it's in this chapter of the book. If it's not, then I'm going to have to do something. Here it is. So you are presented with 3 white solids, is what it says. Oh, and there's another one. Okay, we've got 2 qualitative questions that we can ask. Let's go ahead and look at them. 2 qualitative analysis questions. So first one says you're presented with 3 white solids A, B, and C. And you know that one of them is glucose. You know one of them is sodium hydroxide, and you know one of them is silver bromide. So you know one of them is glucose. What was it? C12H22O11, sugar. Or no, wait, that's sucrose. Glucose is, silly me. Glucose is C6H12O6. So one of them is glucose. One of them is sodium hydroxide. And one of them is silver bromide. Now, they give us a couple clues so we can figure out which one is which. It says solid A dissolves in water to form a conducting solution. Oh, I need to talk about electrolytes before we can do this. Okay, glad that reminded me. We didn't talk about electrolytes. So let me show you a diagram. So whenever you dissolve something in water, you've got 2 main different kinds of soluble compounds. You've got non-electrolytes and electrolytes. Non-electrolytes, an example of a non-electrolyte would be sugar. It's completely molecular, it doesn't break up into ions, and when you dissolve it in water, those molecules, they don't carry any sort of ionic charge through the water, so they don't conduct electricity. Water doesn't always conduct electricity, at least not pure water. The only reason water is said to conduct electricity is because most water, like the tap water that you use at home, has some ions dissolved in it that can carry electricity around. But molecular compounds generally don't dissociate into ions. So if you don't get ions, or you don't get many ions, you don't get electrical conductivity. That's what's called a non-electrolyte. Does not split up into ions, does not form a solution that conducts electricity. On the other hand, you have electrolytes which do conduct electricity, but there are two types of electrolytes: strong electrolytes and weak electrolytes. Strong electrolytes, they completely dissociate into ions, and you get maximum electrical conductivity. Weak electrolytes, in comparison, if you use the same amount of weak electrolyte as you do with strong electrolyte, and then compare them, you can see in that diagram one of the light bulbs is not as bright as the other. The weak electrolyte that you see on the far right, some of it will dissociate into ions, so you get a few ions, but some of it will also behave kind of like a molecular compound and just not split up into ions at all. And we'll dig into the difference between strong electrolytes and weak electrolytes in a later chapter that's more focused on solutions, but for now, just know the basic idea. Electrolytes conduct electricity to varying degrees depending on their strength. Non-electrolytes don't conduct electricity. Okay, and that's all we need to say about that. Now then, back to the clues for this question. So you've got three white solids, A, B, and C. One of them is glucose, one of them is sodium hydroxide, and one of them is silver bromide. So it tells us that solid A dissolves in water to form a conducting solution, conducts electricity. Conducts electricity. It tells us that solid B is not soluble in water. When you put it in water, it doesn't seem to vanish. It doesn't matter how much you stir, it doesn't seem to be vanishing. And then solid C dissolves in water to form a non-conducting solution. Does not conduct electricity. Doesn't conduct electricity. And I think you can already tell which one is which. They made this one pretty easy for us. Does not conduct electricity. Probably should have made more space for that, but if you can look at it, first of all, which one is the one that's not soluble? That's going to be the easiest one to identify, because we know our solubility rules. So glucose isn't going to be a problem, even though we don't have a solubility rule that applies to it. We know glucose is a type of sugar, and we know sugar dissolves in water, so we know the glucose is soluble. Sodium hydroxide, it did say in rule number 6 that all hydroxides are insoluble except when paired with group 1 metals, such as sodium. So sodium hydroxide is soluble. That leaves the silver bromide. Rule number 3 said that bromides are soluble except with silver, lead 2, or mercury 1. So silver is what makes this insoluble. So we've identified AgBr. That's not too bad. Then we've got one of these, both of the other two are soluble, but one conducts electricity and the other one doesn't. So the one that conducts electricity can separate into ions, so it must be an ionic compound. Glucose is molecular, sodium hydroxide is ionic. So the ionic compound must be the one that separates into ions that carry electric charge. And the glucose then must be stuck as a solid C. So that's C6H12O6. Okay, so there's an example of qualitative analysis. Here's another one. So you're faced with a little bit of a problem. It says here that the labels have fallen off of two bottles, one containing magnesium nitrate and the other containing lead nitrate. So we've got two bottles. One of them is magnesium nitrate and the other is lead 2 nitrate. And for those of you wondering, even though lead is technically not in that yellow block of the periodic table, it is still a transition metal. A couple of the metals past the yellow block are still considered transition metals, and I honestly don't know which ones count and which ones don't. In fact, if you go to Wikipedia and you look up what are they called, post-transition metals, then you're going to find that there are actually a couple of different viewpoints as to which ones count and which ones don't. But that's another story. The point is, lead does need a Roman numeral, even though it's not in the official yellow block of the periodic table. Where was I before going off on that little detour? Right, so we've got two bottles. The labels have fallen off of them. One label says lead 2 nitrate, the other label says magnesium nitrate. We don't know which is which because both of those solutions are clear and colorless. So it says you have a bottle of dilute sulfuric acid. Dilute just means low concentration. So we have dilute sulfuric acid. That's something we have available to us, and it's asking how could you use it to test a portion of each solution to identify which solution is which. This relies on the intensive properties of these solutions. Yes, solubility and precipitation are intensive properties of compounds and mixtures, I suppose. So intensive properties don't depend on how much you use, they just depend on the identity of the substances or mixtures being used. In this case, I only need one drop of each to test to figure out which one is which. So they didn't make it too hard to figure out. You take a drop of this and a drop of this and you mix each of those with some H2SO4 and you see which one gives you a precipitate. So sulfates are usually soluble. That's what our solubility guidelines say. Right? Rule number 4 says all sulfates are soluble. One of the exceptions, though, is lead 2. So if I go ahead and mix H2SO4 with each of these, then for this compound I'm going to get MgSO4, which will be soluble, and whichever one is the lead nitrate, I'm going to see a precipitate. PbSO4 is not soluble. So this is going to come crashing out as a solid, and MgSO4 will remain aqueous. And there you go. Once you've done that, you've identified your magnesium nitrate from your lead nitrate, and you haven't wasted too much of either. Those compounds are probably pretty expensive. So it's definitely great that we can use a property that doesn't rely on the actual amount of substance used, because we'd like to use very little just to identify the substance. And that takes care of some qualitative analysis. I know there was another one somewhere, but it's probably not in this chapter. It doesn't look like it. We'll probably see it again in a later chapter. I'm not too worried about it. It was something about separation techniques. But anyway, the last thing I want to do, instead of qualitative analysis, now it's time to do a little bit of quantitative analysis. So there's something called gravimetric analysis. Honestly, I don't think it deserves to have its own unique name, because I think it's one of those procedures that to me is so intuitive and simple. I don't see why it ended up needing its own name, but gravimetric analysis is a quantitative analysis that you can do to figure out the amount of what's called an analyte, the thing being quantitatively analyzed, to figure out the amount of analyte that was present in some sort of compound. So there's a new vocab word for you today. Let me pull out the only gravimetric analysis example that I actually have. Here it is. So the problem is presented to us saying a 0.4550 gram solid mixture containing magnesium sulfate is dissolved in water and treated with an excess of barium nitrate, resulting in the precipitation of 0.6168 grams of barium sulfate. And they give you the reaction below, and they ask us what is the concentration or mass percent of magnesium sulfate. They don't want the concentration in moles, they want it as a mass percent. So you basically have magnesium sulfate mixed in with a bunch of other junk, and we want to know what percentage of this stuff that we have is actual magnesium sulfate. So if you're like a manufacturer and you're trying to extract and mine magnesium, for example, you'd want to know what percentage of your rocks are actual magnesium, so you know whether or not you're wasting time digging that particular cave where this rock came from, or if you should actually start digging more in that cave. So let's see. I'm just going to take down the information before switching back to the camera. So we've got 0.4550 grams. That's your mixture, probably some sort of rock. And that mixture contains some magnesium sulfate. The magnesium sulfate is treated with excess barium nitrate. That way you guarantee that you've reacted all of the magnesium sulfate and none of it is left over. That's very important. Resulting in the precipitation of 0.6168 grams, 0.6168 grams of barium sulfate. All sulfates are soluble, but barium is one of the exceptions. So we've got 0.6168 grams of barium sulfate, and of course there's the equation. They want the concentration as a mass percent of magnesium sulfate in this mixture, which I presume is just some sort of rock that was mined out of a cave. Okay, so if we write down their balanced equation, then I see we've got MgSO4, which was aqueous, plus barium nitrate, which is also aqueous, gives us some solid barium sulfate, of course, and some magnesium nitrate. And it looks like this equation is already balanced. Let's note that that's aqueous. Okay, so just kind of following the logic and making sense of what's going where. So you had some mixture. It had some magnesium sulfate in it. And I suppose they determined beforehand that all the other junk in the mixture wasn't going to react with your barium nitrate. It would be very important for them to check for that, because if you're bringing out more things than barium sulfate, then you're probably overestimating the barium sulfate that you collected. But yeah, there's some magnesium sulfate in there. They somehow dissolve it out, so maybe they just put this rock in water and allow the magnesium sulfate to all dissolve. And then they mix in some barium nitrate. The barium nitrate, of course, will precipitate out some barium sulfate. So any barium sulfate you get, the sulfate in there must have come from whatever amount of magnesium sulfate you had to begin with. So you can use the amount of barium sulfate to figure out the amount of magnesium sulfate you had originally, which you can then go back and use to figure out the percent magnesium sulfate in the mixture. I think that's pretty intuitive. I don't think it's worthy of, having its own name and being called gravimetric analysis. I would just call this clever use of stoichiometry. But what do I know? Okay, so let's go ahead and figure out if we got 0.6168 grams of barium sulfate, then, I'm going to need the molar masses. Let me Google those real quick. Might be faster than calculating them by hand. So, molar mass of, I need barium sulfate and I suppose magnesium sulfate. Barium sulfate. So that's 233.38. 233.38 grams per mole. And then for magnesium sulfate, let's see, so that's, I'm going to need to modify that search. Goodness gracious. I'm starting to regret trying Google. Okay, magnesium sulfate is 120.366 grams per mole. Let's go ahead and figure out what we've got in here. So, if we start with 0.6168, let me do this in yellow. If we start with our 0.6168 grams of barium sulfate, then we can convert that to moles of barium sulfate. Wait, is this balanced? Yes, it is. Okay, just double checking. So we've got every 233.38 grams gives us 1 mole of barium sulfate, and then every 1 mole of barium sulfate gives us 1 mole of magnesium sulfate. And then, of course, every 1 mole of magnesium sulfate is going to be 120, so 1 mole of magnesium sulfate is going to be 120.366 grams of magnesium sulfate. That'll give us our grams of magnesium sulfate. So let's go ahead and calculate that. 0.6168 divided by 233.38, rounding to 4 sig figs, 0.002643. 0.002643 times 1 over 1 doesn't change. Multiply by 120.366 and round it to 4 sig figs again. That's 0.3181. 0.3181 grams. So that's how many grams of magnesium sulfate we got out of our rock. If our rock was 0.4550 grams, then it was 0.3181. That's the part we want, divided by the mass of everything, 0.4550, times 100%. With 4 sig figs, we would say that this 0.4550 gram rock was about 69.91% magnesium sulfate. And there we go. There's your classic gravimetric analysis problem. And with that, you are finally free to go. Not that you're being held hostage, like I said in the last video. Hopefully this was all informative and good stuff. For next time, the plan will be to go over... well, you're going to see some more ionic equations, definitely. We're going to talk about oxidation and reduction some more. We're going to talk about chemical reactivity. And we're going to talk about using half reactions to balance equations and acids and bases and all that good stuff. So that's what's coming up next. Hopefully you had fun learning with this video. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see you in the next video.